Hi, Dave Parker. Can I get a sound check from you, as well as a camera check?
Good afternoon. Do you hear me? Good morning to you.
Yes, Dave. Great. Thank you.
Is picture framing okay for you?
Yes, everything's good.
Okay, cool. Just to confirm that I have a few slides that I will be displaying. Hopefully it should work okay.
Yes, you'll be able to share your screen just before your presentation begins.
Great, thank you.
And Greg, can I get a quick sound and video check from you?
Yeah. How is that, Ricky?
That's great. Thank you.
Excellent.
Recording in progress.
Good day, everyone. We're just about 5 minutes away from the top of the hour. I just wanted to remind everyone that to keep your microphones muted and your cameras off when you're not speaking. And then if you're about to present, you'll be able to then share your screen and open your microphone and start your camera. So we still got about another 5 minutes before we begin though. And we're just about 2 minutes away from the start of our meeting. For those just joining, I'd just like to remind you to keep your cameras off and microphones muted when you're not speaking. We will begin in about 2 minutes. Okay, and we've reached the top of the hour. And so at this time, we can go ahead and begin. I'm just going to hand it over to our hosts today, Greg Schmidt and Mahesh Anand.
Great. All right. Well, thank you so much, Ricky. Welcome to everyone. What a day it's starting out to be. I can't tell you how happy I am today to welcome you to the NASA Exploration Science Forum, which is being held jointly this year with the European Lunar Symposium. It fundamentally now, space exploration is an international endeavor, and I think that it's particularly appropriate that we're holding this jointly with our European partners. And in just a few minutes, my co-chair, Mahesh Anand, will say a few words of welcome as well. Like I say, what a day it's already started out to be. Less than an hour ago, we saw the successful launch and landing of the Blue Origin New Shepard spacecraft. This was a little over 60 years after Alan Shepard's historic flight. And so this means a lot, I think, not just to our community, but to the world. It's way more than billionaires going to space. It's a fundamental change in the way we're going to be doing space. I was particularly touched, as I know so many of you are, by Wally Funk finally getting her historical due and flying aboard this spacecraft. And from the audio that I heard, she was very excited indeed. She, of course, was a member of the Mercury 13 that never did get to their flight in space aboard Mercury, but she got hers today. How wonderful that is. This harkens a new era in space, and one that our community is going to be taking full advantage of and going forward to the moon. You're going to be hearing about that in a number of talks during this conference. So very, very exciting. I should note as well that today is the 52nd anniversary of the landing of Apollo 11 as well, something that has touched all of our lives, whether we were there to experience it or not. So it's really an honor to bring you the biggest forum yet. We have a record number of abstracts. We got 250 abstracts, which was half again as much as our previous record. We also have a record number of registrations, well over 600. So I'm just so pleased that all of you are going to be able to join us for what I know is going to be a very exciting meeting. You've seen the announcements. I will be sending you out a set of announcements every day. Sent one last night. We'll send another one today, and we'll send them each day so that we can minimize the number of things that I have to say at the beginning of the day, and so that you'll all be clued into the many exciting things that are going to be happening. And those are going to be posted on the website as well. But just to highlight a couple of things, first of all, as you all know, I believe, we're doing our posters via GatherTown. And this is something that I will admit that I did not have previous familiarity with. My deputy, Christina Gibbs, who I'd like to acknowledge, who was responsible for so much of this forum, she had done this before, spoke highly of it, and I have learned it myself. And it's a very easy and fun way of navigating around to the various posters and various other things that we're going to be holding through GatherTown. I should note that our very capable IT team has put an Easter egg, actually several Easter eggs there. I won't tell you what they are. You have to find them yourself. So through GatherTown, we are also going to be having office hours. We're really honored to have a number of people from NASA headquarters, both from Human Exploration and the Science Mission Directorate joining us for these office hours. We also have people from the European Space Agency, from the Lunar Surface Innovation Consortium, and from SSERVI. Christina and I will also have office hours. So I hope you feel free to join us there and just ask us any questions you might have. We have networking opportunities as well. And then one other thing that I really want to highlight, which we started last year, is, and I'll talk about in just a second, is that we have a set of plenary equity, diversity, and inclusion talks. So that brings me to the organizing principles for this conference. We want to bring you, first of all, the best science we can in the best way we can do it. And that's number one. Number two is connecting people as best we can virtually. We are close to 18 months into this pandemic right now. I hope that we're seeing the end of it in sight, but we've all had various difficulties that have hit all of us, and in particular, we haven't been able to connect with our friends and colleagues in the community, and so we're trying our best to help you do that. And then the next one is creating opportunities for the next generation. And I would say that arguably the next generation has been hit disproportionately with through the pandemic. And I think that we really owe it to those who will be the next leaders sooner than we think, to create the opportunities we can. And so we've done things like having next generation co-chairs for all of our sessions and other things. And then one other organizing principle that I want to really highlight is equity, diversity, inclusion, and accessibility. And you see an interpreter next to me, which I'm very happy to have her join us. And thank you. And so what this says is that I think, to me, our priorities with SSERVI, our priorities with the community, that bringing in a more inclusive approach, bringing in a broader swath of the populace, both in the United States and the rest of the world, is as important as anything else we're doing. And I have a vision for a broader community that we can all work together to help create. So with that, I would like to introduce my conference co-chair, Mahesh Anand. In manner of introduction, Mahesh and I first met 13 years ago at our very first event, which we called the Lunar Science Conference back in those days. And this meeting led to a partnership between then the NASA Lunar Science Institute, now SSERVI, and the United Kingdom, but also a vigorous partnership between NASA and the Europeans, focused on all the great things that we do. Mahesh is a noted lunar scientist and a leader of the community, and he's based at Open University. So Mahesh, please.
Thank you very much, Greg. So what a wonderful introduction you have given, and I'm just so proud to be here with you all. It's a good day to everyone, wherever you are joining us. I hope you can hear me okay. First of all, I just wanted to thank SSERVI, especially Greg and Christina, because they were the one who actually entertained my idea when I proposed that for this year, would it be possible to combine the European Lunar Symposium with the NASA Exploration Science Forum? Because what I felt that because of the ongoing pandemic, we weren't able to meet in person, but also we were getting a bit tired, if I may say so, of too many conferences to regularly. So what we thought was, can we actually try something different? And I'm so pleased to see that actually, you know, that has resulted into what you are going to see over the next 4 days. And I also would like to acknowledge the two co-chairs of the Science Organizing Committee, Caroline Wonder-Bogart and Parvati Prem. I think they have just done a Herculean job in really putting together this program from all aspects. So I think, let me not forget to thank them. You know, I can't thank them enough. And together with Christina Gibbs, I think they have given both Greg and I plenty, you know, to take off our shoulders. And then we just knew that this was all going to work out. So I'm absolutely delighted, and I'm really proud to see how this has evolved. And I do hope that you really enjoy this meeting, which Greg has already pointed out. It is very much about the science, but it's not just about the science. It's about bringing communities together. And bringing communities together in a very inclusive way so that nobody is left behind. And I think as we go forward and we get over this pandemic, when we restart some of the in-person meetings, I hope that some of the good lessons that we are learning along the way, we will not forget those. And we will actually introduce them in our day-to-day you know, lives. And that's the only way to make real progress in the society, in my view. So, you know, with all that, I think the only other thing I wanted to say is I'm simply a mouthpiece here for the European community. And I'm speaking on behalf of all the PIs of the other European SSERVI nodes, who obviously can't be here. But it is something that we have built together with NLSI, now SSERVI. And this would have been the 9th European Lunar Symposium had it taken, you know, place in person. Last year it was going to take place in Padua, and at a very short notice we turned it into a very successful online meeting. And if I'm not wrong, that was probably the very first online meeting for planetary science community. And this year I think we are trailblazing a completely different way of organizing conferences and meetings. And I do hope sincerely that next year we would be able to welcome many of you in person, in Italy, in Padua, and fingers crossed that we can get over this pandemic. But nonetheless, as I said, we will still try to implement all of the lessons that we are learning through this conference to make it even better in future years. So I think with that, I would like to move into the plenary. Greg, if that's okay. Great, thank you. So we are slightly ahead of time, but I hope that nobody would mind getting started a little bit early. We already have almost 200 participants, and we have a very busy program. So it's my great pleasure to be able to introduce the first speaker of our plenary, Dr. David Parker. Dr. David Parker is the director of Human and Robotics Exploration Division at ESA. Dave and I go back probably over 10 years. I first met him when he was working for, well, it was not yet the UK Space Agency, what then became the UK Space Agency. And Dave moved on to ESA in 2016. And for the last 5 years, he really has been spearheading the European Space Agency's effort to reach to the moon and not just stop there, but actually go beyond to Mars. And he will be actually telling us everything that he has been trying to do and would like to achieve in just 10 minutes. So Dave, are you ready?
Thank you very much, Mahesh. Yes, thank you for that nice introduction. And thank you, Greg, also for the chance to be here. I hope you hear me well. Anyone that has seen my talks knows that I always have slides and probably too many, so I apologize in advance. I really want to thank the organizers for organizing such a wonderful transatlantic event and for the chance to talk to you this morning or this afternoon, depending on where you are. So let's see if I can get my slides working, because there's always a different tool. So let me just check whether you can see my slides okay. We do. Okay. In display mode. Right, here we go. So I want to do 3 things today. Maybe explain a little about our overall exploration program, describe the role of the moon in it, and finally to emphasize the people who underpin the activities that we're now underway. And like you say, I'm supposed to do this all in 10 minutes, so that's going to be a challenge. I better get going. Now, I always like to start these talks by saying that space exploration offers a unique combination of curiosity and opportunity. Curiosity to venture into the unknown, and the opportunity to bring back to Earth discoveries and skills only possible by exploring with humans and with robots. Now, Europe's space exploration program, now named Terra Novi or New Worlds, is based on expanding the human presence from low Earth orbit to the moon and to Mars, working with international partners and with our industry across Europe. Now, through the International Space Station, low Earth orbit has proved its value as a place for humans to live and work. Right now, a European astronaut with a French passport, Thomas Pesquet, is hard at work on the station on his Alpha mission. It's the patch I'm wearing today. But he's following dozens of astronauts who have performed hundreds of experiments on behalf of thousands of scientists across Europe and indeed the rest of the world. I don't need to explain to this audience that the moon has immense scientific and practical potential, and it's the next place where humans will live and work. But of course, the red planet is a key science target because it's got much to reveal about the potential for past or present life elsewhere in the universe. And so we have this program that tackles all 3 destinations in an integrated way based on 4 cornerstone exploration campaigns and underpinned by enabling technology and the utilization and science actions that get the value out of what we're trying to do. Now, this slide explains the concept, but I'm only going to focus on the lunar exploration for the rest of this short presentation. In terms of the hardware, this picture kind of captures the jigsaw pieces of ESA's current and near-term lunar exploration activities. But a picture perhaps misses the underlying strategy, which is crucially built around a balance of scientific and economic goals, a recognition of the important inspirational value of what we're doing, and I'll come back to that later. But last but not least, the international dimension, and that's already been mentioned. ESA, European Space Agency, is an organization of 22 countries working together. Actually 25 when you include the cooperating and associated states such as Canada. So melding different cultures is in our DNA, and we enjoy working with countries as diverse as the US, Russia, China, and Japan, and we're doing that today. But for example, ESA is proud of its partnership with NASA on Artemis, and we're now building 6 European service modules for power and propulsion for Orion. ESM #1 is at the Cape right now, preparing for launch as part of the Artemis 1 uncrewed demonstration mission. and ESM-2 that will propel astronauts in deep space for the first time since Apollo is being prepared for delivery later this summer. Going forward, Europe is building 2 out of the 4 modules of the Lunar Gateway, the first permanent outpost around the moon, and a base camp for sustained lunar exploration. We're doing telecommunications, we're doing habitation, we're doing refueling technology. The first elements are already in manufacture across Europe, and 3 European astronauts will fly to the Gateway before 2030. Okay, so much for some of the hardware, but what are we actually trying to achieve by our lunar exploration? This slide tries to explain. I always call the Earth the 8th continent, and it's my cliche to call it a museum of 4.5 billion years of solar system history. And you know better than I that it has recorded this history perhaps more completely, more clearly than any other planetary body. And this is why, going forward, I believe that as today we have Antarctic research bases where some of our astronauts work themselves, I'm convinced in the future there will be at least one international research base on the moon, perhaps monitoring and understanding our own star, the sun, looking back to the dawn of the universe with radio telescopes, and learning how to use the moon's resources to make exploration more sustainable. And therefore, to prepare for that, ESA is already studying further contributions to lunar exploration. And I'll highlight 2, a multifunction lander called EL3, and a network of lunar communications and navigation satellites called Moonlight. So first, here's EL3 as it is today. A paper concept that we're defining with industry. 2 studies are ongoing. It's a kind of 1.5-ton pickup truck, a step beyond the small landers currently under development, but able to reach more remote areas when compared to a large human lander. Applications could include landing cargo to support astronauts, but also undertaking ambitious lunar polar missions for science, and even acting as providing an early demonstration of radio astronomy on the far side of the moon. Equally, if we're going to have sustained lunar exploration, we will also need permanent infrastructure, and that includes flexible communications and navigation capabilities, again for both humans and robots, and the 2 of them working together. This is an area where we believe that private entrepreneurs can play a strong role. So we have supported the commissioning of the world's first commercial deep space comms antenna, communications antenna, located at Cornwall in the west of England. It's already being tested with Mars Express at one of our other missions, and it will be used to support the Artemis 1 CubeSats. In a second step, a European company, Surrey Satellite Technology, is building Lunar Pathfinder, a kind of Swiss Army penknife, a small orbiter around the moon, which will do a key test of navigation, trying to use the navigation signals from Earth satellites. It carries a space weather payload and even a laser retroreflector from NASA. But importantly, we are planning to buy a service and not the spacecraft. And a further step is an operational constellation for lunar comms and nav, and this is being defined by 2 commercial consortia right now. Now, time doesn't really permit me to go into the full range of science and technology topics that we aim to enable with our program, so I just focus on space resources for today, and please don't think that all the other science topics are unimportant. Our strategy for space resources contains these elements you can see now, which are being implemented step by step. But as one example of hands-on research is illustrated here with the space resources, a demonstration of extracting oxygen and titanium from the simulated lunar regolith. But ESA colleagues are also participating in the Apollo next generation sample analysis research work also. So there's a lot going on, and I've hardly covered it. But as we're all reflecting on the past strange 18 months and why we're doing what we're doing and how we came to be doing it. So apologize if I come to the end here with a bit of a personal reflection. As I was preparing this talk, I reached out to the shelf above my desk where I keep files of old magazines, photos and books. So from one file, I pulled out an envelope of yellowing information sheets and a photo of a moon rock. I realized with actually quite a shock that it's exactly 50 years since the theme of the annual show of my home city, Liverpool, was the close historical bond between this English city and the United States. Now, in the previous decade, Liverpool had changed the world by exporting the Beatles. In 1971, a piece of a new world, the moon, came to Liverpool. And so it was that the 8-year-old me was pressing his nose against the glass box in which it was displayed. I also got to see the Apollo 10 command module that was there as well. So I know it's 50 years ago because one of the information sheets says Apollo 15 is going to lift off on the 26th of July, 1971. So the point of this trip down memory lane or amnesia avenue is that the future of lunar exploration lies not in the hardware, but in the software of the explorers. People like ESA researchers Beth Lomax and Alexander Maurice, who carried out that test of oxygen extraction that I showed you moments ago. Now, I'm just a second-rate engineer who's become a third-rate administrator. But if I can do anything, it is to help prepare a future of lunar discovery and inspiration that will write new chapters in this unveiling of our 8th continent and hopefully inspire long after I have gone. But it is up to you, dear conference participants, dear symposium participants, who will do the real work. So please have a great conference. And if you have been, thank you for listening.
That's great. Thank you so much, Dave. As always, you are so inspiring. And I think that if the other 200 people who are with me, if they aren't inspired now, I don't know when they would be. Fantastic, and all the best with the various ESA projects that are taking off. And I know that we didn't do justice by just having 10 minutes for you. But that's a great way to start the conference. Now we have a couple of minutes to spare. Are you planning to stay around, Dave, at all, in case people wanted to ask you a couple of questions later, or do you want them to ask now?
I'm at your service, completely at your service. I'm here now. Or later.
Right. That's great. So I think if anybody has any questions for Dave, perhaps this is the time to ask it. And so maybe you unmute yourself, identify yourself, and ask the question.
And you can also put them in chat.
I think everyone's stunned. I'm just the warm-up act for Jim Green anyway.
I think we are going to get some questions your way for sure, Dave. So no, thank you. Thank you once again for accepting our invite. I know that you have a busy schedule. And thank you.
I'll be here for another 45 minutes or so. That's
great. Thank you. So I think with that, I'm going to hand you over to Greg, who will introduce our next speaker to you. So Greg, over to you.
Great, thanks, Mahesh, and Dave. Thank you so much for a really inspiring talk, particularly that conclusion you gave. That was just wonderful. So I have the honor, and I'm absolutely delighted right now to introduce Dr. James Green. Jim is the Chief Scientist for NASA. I also, by the way, want to welcome Dave Draper, his deputy, who is with us as well here. Jim served, in addition to or prior to his role as Chief Scientist for NASA, he served as Director of the Planetary Science Division within the Science Mission Directorate for a decade, and during which time he oversaw the creation of the NASA Lunar Science Institute, which became SSERVI. So we know each other well, and I count Jim as a good friend. And before that, he was at Goddard Space Flight Center. His background is in heliophysics, and his talk is entitled Our Rare Moon. So Jim, over to you.
Thank you very much, Greg. Let me go ahead and bring my slides up. All right, and start them. Here we go. Okay. You know, this has really been a fantastic era, you know, with over 4,500 exoplanets have been found, but no moons have yet been uncovered. But we do expect that to change in the future. The discovery of exomoons around terrestrial exoplanets will help determine how rare they really are or common, providing us an understanding of how special our moon may really be. Now, one of my favorite books in astrobiology is by Peter Ward and Don Bromley. It's Rare Earth. And indeed, they propose that our moon plays a number of critical roles in keeping the Earth uncommonly habitable. Since it provides lunar tides, it stabilizes the Earth's spin axis, and it slows the Earth's rotation rate down. All believed to be important for the development of complex life. It has made us what we are today, the inquiring species that is enabling us to look back at the moon to determine what will be our future. In other words, I think Don's book and Peter's book should really have been called Rare Moon. In fact, we know the moon is a witness plate for the bombardment history of the inner solar system, but can it provide us with more details? And we resoundingly realize, yes. It enables us to understand perhaps that early Earth-Moon evolution, let alone as we, with the Artemis program and others joining us to go to the moon and explore, will be a key location for us to launch into discovering much more about our solar system and learning to work on planetary objects. Well, the moon has provided us a number of stabilities. Here are the Milankovitch cycles. The key one that changes our climate on a regular basis. The eccentricity of our orbit changes due to the pull and tugs by Jupiter. We have the precession of the equinox. The moon is intimately familiar with making the Earth tilt axis stable, moving it only from 22 degrees to 24.5 degrees. And even that makes major changes in our climate. When we look at other planets that don't have, indeed, a stabilizing moon like Mars, the obliquity of Mars is absolutely enormous, as shown here over the last 10 million or so years, varying from 48 degrees to 15 degrees, whereas you also see that the Earth's axis is, and its obliquity is incredibly stable. Some of the new research that has gone on in terms of studying the lunar samples that have come back has really been able to tease out that magnetic history of the moon, showing us that perhaps the moon generated internal magnetic fields that created magnetospheres early on, which rapidly then decayed at about 3 billion years ago. Now, this has allowed researchers to really take a look of what that magnetosphere might look like as it couples to our own magnetosphere in the early Earth formation period, as the moon was created outside the Roche limit from the giant impact hypothesis, and then began to move ever increasingly away. But while it had a magnetosphere, it had an opportunity not only to protect the Earth once again, making it uncommonly habitable, perhaps, along that theme, but allowing through connected field lines for evaporated atmosphere coming from the Earth to the moon to be stored in its polar regions. Also, new results indicating, as we look at the polar regions and the possible hydroxyl or water content and the oval shapes of that we see in both northern and southern hemisphere has been put together as an understanding of perhaps the tilting of the lunar axis over time due to the late heavy bombardment and magma moving out and filling in, creating the mare, changing the mass distribution and tilting the axis perhaps by as much as 8 degrees. In addition to that, this is also an era for which perhaps as this intense period of bombardment and then volcanic release of gases building up an atmosphere perhaps as large as 10 millibar, which is even larger than the current moon's or current Mars's atmospheric pressure. We need to tease these things out to find out how they really occurred over time. In addition to that, the LADI observations, as it looked in its low lunar orbit for a variety of dust, but also the final outgassing of the moon that continues on, it sees these water signals that have been traced, of course, to micrometeors that have been impacting the moon and creating these clouds of water, which then, as they get ionized, are pulled away, or as they are able to move to cold traps, end up once again in our permanently shadowed regions. So with these new findings, what can it tell us? What is the history of the early Earth moon? May it look like this? We can perhaps uncover it by going into these permanently shadowed areas, both in the North and South poles, coring down and really teasing out this volatiles evolution that we believe has been occurring. So perhaps we'll see the early comet and asteroidal volatiles that happened in the very early stages of the solar system. Then again, the lunar atmospheric volatiles. How much did the moon outgas during that time? With connected magnetic fields, perhaps volatiles from the Earth. Nitrogen, oxygen. We know nitrogen is also embedded in the regolith. We have found that before, and we therefore think that there's been some sort of communication between Earth atmosphere and the moon. Perhaps the magnetic field really enabled that. And then, of course, for the last several billion years, 3 billion years or more, the lunar water cycle from micrometeors. Now, all this will be mixed up, as we know, the bombardment history of the moon and micrometeors, the constant gardening that are going on. But if we're able to get into these permanently shadowed regions and core them in such a way that we're able to at least tease out some of these elements over time, then the new secrets about our early evolution of the Earth and the moon can be revealed. But it doesn't stop there. In reality, the moon is a major part of our future. As our programs are now moving, more humans will be exploring beyond low Earth orbit. We want to be able to stay on the moon for longer periods of time than the Apollo. We want to be able to build infrastructure. We have the opportunity in really utilizing the resources that we're finding on the moon to build fuel depots or to be able to mine and manufacture in the area and begin to learn to live and work on a planetary surface. So the moon, as rare as it might be, is really there as a stepping stone for our future, but also illuminating all its secrets for us to determine about the past and how we became uncommonly habitable here on Earth. Thank you very much.
Wow, Jim, thank you. That was outstanding. How lucky we are to have both you and Dave Parker introduce this conference and provide that kind of a perspective. And the moon, of course, is interesting in its own right. That is what a large part of this conference is about. But to link it with us in such a direct way is just wonderful. So thank you very much. And let's since we do have at least 3 minutes before our scheduled next speaker, let's take a bit of time for questions. And I think probably the easiest would be to put it in chat, and then either Mahesh or I can read the question. So let's do that. So one question is about the Gravity Assist podcast, and that's for you, Jim, asking whether you host that, if you want to say a word.
I do. Well, thanks so much. Yes, several years ago, I had an opportunity to work with NASA Office Communication to explore a new medium in podcasting. And so Gravity Assist has been one of the most popular podcasts NASA has, and we're going into our 5th year. And this year, we're looking under the hood at NASA, talking to people that are behind the scenes that are really making the spectacular missions and activities happen. And it's really been a delight to do. So I hope you enjoy it. Thank you.
Great, thanks. And here's another one from Simone Dell'Agnello. Let's see, great talk. Interesting how differently the obliquity of the moon impacts the Earth as opposed to Mars, Phobos. Can you comment on Phobos and Mars?
Well, the Japanese will be our first great attempt to go to Phobos and bring back a sample. Their mission called MMX, this is the Martian moons exploration mission, will both visit Phobos and Deimos, orbiting them for a period of time, but then setting down on the surface and bringing back samples. And we need those to really understand whether they're debris left over from accretion of Mars, or impacts that have put material in the equatorial plane that have pseudo-accreted into these small objects. Phobos and Deimos are 20 kilometers or less. Or are they captured asteroids? And so the sample return mission will really tell us. But they're not anywhere near what our moon does for us.
Yeah, that's for sure. So let's see. Here's one from. We'll take 2 more questions. Here's one from Carolyn Vander Bogert, who I want to note is, as Mahesh said, is one of our SOC co-chairs responsible for this conference. So for both Dave and Jim, and let's maybe start with Dave on this one. Do ESA and NASA have plans to collaborate with the Chinese Space Agency on their International Lunar Research Station?
Thanks. Yeah, it's a great question. So I guess we've been talking to CNSA for more than 2 years on the International Lunar Research Station, discussing possible collaborative opportunities. I can say that nothing concrete has emerged yet, but there are some European payloads that may fly on Chang'e 6, and that may lead to some engagement of ESA in that particular mission. But again, nothing has been decided. It's a little bit up to our member states. I always have to explain that what I want to do is irrelevant. It's what our 22 member states want to do that is the final decision-making body. So yeah, watch this space.
Yeah, relative to NASA, we have, of course, legal restrictions working on a bilateral basis with the Chinese, but we have no restrictions working with them in a multilateral setting. And indeed, the restrictions bilaterally are such that we define our interactions with them, and then once approved by the administration and Congress, then we execute them. And we have done that on a number of small activities with the Chinese directly.
Great. Thank you both. And then let's take one last question, even though it'll make us a minute or 2 late. And that's to Jim from Clive Neal. What is your vision for making human exploration of the moon sustainable?
Yes, the sustainability part of it is really critical, and we must really think about a capability where humans can actually live there. So that means, what do they take? What they take must be reused. how they can shape the environment to then support their activities there. Things like we would use with 3D printing, the ability to create an environment where we can land and then be able to move to a habitat, be able to grow food on the moon. The concept of starting that process of learning to grow food on another planet and then be able to harvest that. The moon is close enough that we can be supplied with food over periods of time, but we'd be remiss not really moving briskly in that particular area, because going to Mars will depend upon the ability to really grow much more food to create a sustainable activity. All kinds of life science investigations we want to be able to do. We know how humans survive with our microbial support. Microbes gut microbes in astronauts on space station change. I assume they'll change on the moon. And how will they? And can that be important in terms of eliminating toxins and other things that are different in that environment than home? So there is a whole variety of things that we have to do research in these areas to really create a sustainable working relationship on the moon to then begin the process of bringing in more heavier manufacturing, much more concepts about building larger structures, and using the moon as a vantage point to then continue on exploring the rest of the solar system. So it really provides and is a key location for us. We are so lucky to be able to have it there outside the huge gravity well of the Earth. We have a lot to learn by going there. We need to do it.
We sure do. We sure do. All right. Well, on behalf of our 225 participants right now, let me thank both you, Jim, and you, Dave, for fabulous talks. Thanks again for opening the conference in such a wonderful way and being accessible to everyone. Really appreciate both of you being here. Thank you. So with that, I am going to introduce the next handful of talks and then turn it over to my conference and session co-chair, Mahesh. And our first of those talks is going to be given by Dr. Noah Patro. And it's on the Lunar Reconnaissance Orbiter in the age of Artemis and CLIPS. So Noah, take it away, please.
All right, great. Well, thank you so much, Greg and Manesh. I appreciate being in my basement with all of you today. Welcome. And of course, today is a day we look back and we also look forward. And looking back 52 years ago at this moment, the Apollo 11 crew is in the 11th of their 31 orbits. Shortly, the crew would separate and Buzz Aldrin and Neil Armstrong would make their way down to the lunar surface. And so as we look back on what we accomplished, we also can take a moment to look at what we're doing right now. And this is the quick map view of the moon. And what we're seeing is, of course, LRO is currently orbiting the moon. LRO is flying over the lunar far side right now, right along the terminator, and about to pass over Mare Moscoviense. And so if you allow me now to transition gradually over to my presentation, what I'd like to do is talk a little bit about the future of LRO. Where are we going? And a little bit of where we are in terms of the status of the spacecraft. And so, of course, July 20th is an auspicious day in exploration. And what we've done now at every lunar science and now an exploration science forum is have an opportunity to talk a little bit about what we're doing with the spacecraft, what we're doing with LRO. LRO is nominal. NASA speak for everything's going well. The last year has been remarkably challenging, and the LRO team, both the engineering team, the science teams, have met the challenge exceptionally well. Since March of last year, we have effectively had a small core group of people who have occupied the operations center at NASA Goddard. And the rest of us have been working remotely 100% of the time. LRO is not designed to be operated in this manner. And of course, we met the challenge. Incidentally, in my presentation today, I'll have kind of in the old school LPSC style, one half of my slide talking about the points I want to make. And for those that want to listen with one ear and pay attention with their eyes, some recent highlights from LRO, because as much as we've all changed, the science results from LRO continue marching on. One point I did want to make about how we operate the spacecraft during a pandemic is that, you know, it's not just the operations team at Goddard or the science team scattered around the world. It's also the ground network, the stations around the world that have continued to operate under remarkable challenges. And what I've become amazed by is during the worst portions of the pandemic, the Deep Space Network station in Madrid continued to operate. It was nothing short of a miracle, I think, that the entire endeavor continued on. Our White Sands antenna in New Mexico, our one link to get data down from the spacecraft, has continued on. We've learned how fragile this Earth is, and the networks that we rely on are during the pandemic, and that network has remained strong. In May of this year, we had a lunar eclipse. It was our first total lunar eclipse since January of 2019. LRO, as we've done a number of times, went through power reducing operations. We did keep Diviner on to continue to make thermal measurements of the surface to record the cooling of the lunar surface during the eclipse. It was an exciting observation that we were able to do because we have a robust system that we monitor quite closely. Right now, we're in preparation for our next extended science mission proposal. It's due January 18th of next year. And this proposal would cover us from September of 2022 through September of 2025. Right now, LRO has about 15 kilograms of useful fuel on our spacecraft. Depending on our use of that fuel over the next several years, those include things as phasing our orbit for eclipses, changing our orbit to be in a better position for science observations. We have as much as 7 years of fuel to use ahead of us. Currently, our inclination, that is our tilt away from the pole, is at about 85.5 degrees. And so this means that we will gradually continue to move away from the pole over the course of our next extended science mission. What this does is densify our coverage over the South Pole, and that coverage continues to take us over the so-called Artemis zone of 84 degrees and poleward, letting us build an incredibly robust data set, allowing us, as Jim alluded to understand this remarkable polar environment. As you'll hear in the next set of talks in this session, the future of lunar exploration is remarkable. We have a number of lunar missions that are coming to join LRO in orbit at the moon, as well as obviously missions to the lunar surface. And so this next fleet of missions to the moon joins the recent flurry of activity at the lunar surface. And I take great pride in that LRO has been there for the duration of this sort of renaissance of lunar exploration. Our data and our observations become this thread of understanding all of the data sets. The one unifying factor apart from the moon is the coincident observations of LRO. Whether it's the understanding of the dynamics of the lunar exosphere or the radiation environment, LRO provides this baseline for observations with the rest of the mission. As I said before, we are preparing our next extended science mission proposal. We have 5 main themes following the science themes of volatiles and external interactions. That part of the proposal is being led by Angela Stickle. Regolith and cratering on the lunar surface being led by Catherine Elder. Volcanism in the lunar interior by Julie Stopar. And our support of missions, identifying landing site, characterizing the lunar surface for these missions being led by Maria Banks and John Keller. And so this new era of LRO is partnered with this new era of lunar exploration, and one that I'm particularly excited to look forward to. This morning, we all witnessed something quite remarkable occur out in West Texas. And so I actually changed the quote that was at the top of my slide here. This new era of exploration, I think, is one that obviously we are excited to be part of as scientists and as engineers. But we also look for others to join us in this new era of exploration. And the next decade of lunar exploration is going to be incredibly profound in its terms of discovery and the excitement. And so I encourage everyone to participate in any opportunity to communicate that excitement to the public, particularly through International Observe the Moon Night later this year in October. Later this month will mark 50 years of exploration since Apollo 15. And that moment of science and exploration joined together is one that I hope that LRO continues that proud legacy and over the next many years to come. With that, I'll conclude and have time for questions, or can transition to the next speaker. Thank you.
Noah, thank you so much. And it's hard to imagine doing what we're doing now, progressing towards Artemis and moving towards CLIPS just later this year without LRO and all the absolutely amazing science that it's given our community. So I know on behalf of everyone here, thank you very, very much for your leadership and your team's contributions. It's just been absolutely fantastic. So I think that with that, what I'm going to do is just progress on to the next speaker. If I could ask you and the others to hang on, and then we'll take questions at the end of the session. So now we are honored to have Professor Bethany Ehlmann. Dr. Ehlmann is a professor of planetary science at Caltech, and she is going to be talking about Lunar Trailblazer. Bethany, please.
Okay, thank you very much, Greg, and the organizers. Can I confirm that you can both hear me as well as see my slides in presentation mode?
Yes, thank you.
Okay, fabulous. Well, I'm honored to, as principal investigator of Lunar Trailblazer, I'm honored to present at this forum following on the legacy of the LRO orbiter. We will be a small satellite for lunar water and lunar geology, and on behalf of my team, I'm thrilled to tell you a little bit more about our mission and our progress. We are a confirmed NASA simplex mission. It's a Class D mission. And you can see the beautiful rendering of our Lunar Trailblazer spacecraft here made by Lockheed Martin. We travel to the moon as a rideshare mission on an ESPA Grande ring, and you can see solar panels folded up, comfortably nestled here in the ESPA volume. We travel to the moon using a hydrazine chemical propulsion system and insert into a 100-kilometer polar lunar orbit, where for over a year we'll do science mapping of the moon with our two instruments that are sensing reflected visible and shortwave infrared light and emitted thermal radiation from the moon. The flight system is on track for delivery in October of 2022, and we launch on the IMAP mission. I'm the PI, Rachel Klima at APL is the deputy PI. Our project management is at JPL. Lockheed Martin, as I said, is making our flight system. And then you see our two beautiful instruments, an imaging spectrometer that gets 50 to 90 meters per pixel in over 100 channels of light to sense this 3 micrometer feature due to water. And then the lunar, and that's provided by JPL. And then the lunar thermal mapper from the University of Oxford that has 15 channels for temperature and composition, again, at sub 100 meter per pixel resolutions to get at the temperature of the surface. Now, where are we in our timeline? Well, I am thrilled to say that in spite of a global pandemic, I have a team that perseveres, that communicates well, and we are on track, on schedule, in spite of that. And so a huge thank you to our team in figuring out ways to work together. We have just passed the milestone of our critical design review, and so are now onward to fabrication. Bits of hardware are arriving all the time, and it's really quite exciting that in 15 months, we will have our flight system assembled. So at the moment, NASA has manifested Lunar Trailblazer on IMAP, which launches in 2025. There's a lot going on at the moon beforehand, and NASA has been considering earlier launch options. But when we launch as a part of our ESPA rideshare, we will then travel 5 to 8 months to the moon, after which we will embark on our 1-year science mission for mapping the form, abundance, and distribution of water. How do we do that? Well, it's these nested data sets from our two instruments. So we have simultaneously acquired an hyperspectral image cube and a multispectral thermal mapper cube. So for each pixel, we get a spectrum of the form of water and of the absorption band depth that allows us to calculate the abundance, determine whether it's ice or adsorbed water, and then simultaneously nested in those pixels, we get the temperature. So this is really the key to our mission, is those simultaneous quantities, and we get those in targeted spots around the moon. Here you can see the target density for the permanently shadowed regions along an exemplary lunar trailblazer ground track. So there are 4 goals, but the way to think about them is there are objectives related to water on the sunlit moon, form abundance distribution, and then importantly for science, how it varies as a function of latitude, soil maturity, lithology, and time on the sunlit moon. And then for the shadowed moon, where is the ice? How much is there, and which places are full of ice and which are empty, and why? And so that's tracing ice abundance and temperature. And then along the way, we get some awesome compositional data for those of you interested in lunar crustal evolution. So I'll take the remainder of my time to talk about the top 5 advancements that we expect lunar trailblazer to provide. The first is the form of water on the moon. So especially on the sunlit side associated with these micro cold traps, there's really this question of, is it ice or is it loosely bound water? You can see here as we transition from blue to gray, how Lunar Trailblazer in its HVM cubed instrument adds the additional spectral channels to fully capture that 3 micrometer feature to distinguish the form and abundance of water. Next, the question is, why is the water more enriched in some areas and at some times than others? So we'll be targeting some of these locales where water enrichments have been reported. We'll be looking at 3 times a day for several of our targets to assess change as a function of morning, afternoon, evening. Where is the water changing with time? And then we'll be looking as a function of latitude. And all of this is important because temperature matters. And those of you who are savvy to this know that as we look at this 3 micrometer feature, it's influenced by what's going on at the longer wavelengths. As we move into daytime lunar temperatures, you can see that shape is changing, making Lunar Trailblazer's simultaneous composition and temperature data with its 2 instruments all the more important. I think for the plans that David Parker and Jim Green talked about, among our most important data are those we'll get at the poles from the permanently shadowed regions. In orange, you can see exemplary, our 2 footprint sizes superimposed on Cabeus crater. Within those footprints, we'll be getting at where is there water on the surface to sub 100 meter per pixel levels to 500 meter per pixel levels, depending on the light level. This is very important for the question of which of the cold traps actually host liquid water, how much, where exactly, because this is where we'll guide our future rovers and landers. You heard Jim allude to this question. The other question is, how pure is that ice? Is it like the organics, the cold traps on Mercury, which of course are very rich repositories of organics delivered to the inner solar system? We don't know right now, and Lunar Trailblazer will provide the spectral data in this key wavelength range to answer it. And then finally, the other set of discoveries I expect our mission will make is regarding the silicate composition of the moon, crustal evolution, the history of volcanism. We have potentially ultramafic rocks. We certainly have high silica units. We don't know quite how these relate to volatile content and evolution. And one of the key aspects of Lunar Trailblazer is we'll get compositional data that allow us to distinguish some of these more extreme lithologies that the diviner discovered on the moon. So with that, I'll wrap it up and say that our focused science investigation is really geared toward identifying the best exploration sites on the moon for future landed reconnaissance and answering fundamental questions about the lunar water cycle. We're on schedule, on track for an October 2022 delivery of our flight system, at which point we can start collecting data to support all of the future lunar missions. Thank you.
Fantastic. Professor Ullman, thank you so much. This is such an amazing mission. And as a former mission person myself, I just can't imagine the leadership challenges in dealing with getting all the hardware delivered on time, finishing the design process, et cetera, and on top of a pandemic. So what an amazing job, and thanks for your leadership on this. The community is going to be very excited and grateful when this gets orbiting and gets its results. So what an exciting mission. Thank you. And if you wouldn't mind staying on till the end of the session, great. Thank you so much.
Thank you.
So our next speaker is Dan Andrews, and Dan is the mission manager for Viper. Previously, he was the mission manager for the LCROSS mission that we're all very familiar with, and he is going to be giving a status on Viper. So Dan, please take it away.
Very good. Let me get this going. Says I can't share my screen while other participant is sharing. If someone could lighten that up. There we go. Very good. Can you see the screen okay?
Yeah, I can see it just fine, Dan.
Great. So it's my pleasure to be here talking about the Viper mission and giving a mission update. I also want to acknowledge LRO as well. It's a full circle for me. When we led the LCROSS mission, we were, of course, a co-manifest with LRO all those years ago. And now we're kind of going full loop, going back to the moon again and doing more detailed investigations of what both LCROSS and LRO had discovered and continue together. So Viper, which is Volatile's Investigating Polar Exploration Rover, is part of the overall Artemis plan to return humans to the moon and to enable them to stay. Of course, you don't need Viper to be able to get humans successfully to the moon, but you may need what Viper has to learn about in situ resources in order to be able to support humans for the long term. Viper mission parameters, we're nominally about 100 Earth Day mission, but that's going to be a function, of course, of the actual traverse and site selection that we make. You're going to be hearing a lot more about that from Cola Creek coming up right after my presentation here. We're carrying 3 different instruments, but really 4 instruments. 3 of them are spectrometers, a neutron, near infrared, a mass spectrometer, and then we have a 1-meter drill that we're getting commercially that, of course, is going to be able to bring up materials from below in order for us to understand both the horizontal and vertical distribution of water and other volatiles. Number of subsurface assays or drill sites that we plan to have. We think we need about 18 in order to be able to get the right statistical makeup in order to make our determinations about the different ice stability regions that, again, you'll be hearing more about coming up. But we think we'll be able to do many more drill sites than that, which will only make our data more robust. The key driving energy cases for our design have to do with dark survivability and the permanently shadowed region working duration, meaning with drill, all the instruments, locomotion, getting in and then getting out of the PSR. And so those 2 parameters, as you can see there, nominally 70 hours at this time, 12 hours. Those are key driving design capabilities. And as we're about to approach our CDR in the fall, these will get locked in, the correct values will get locked in, and then, of course, we will optimize the mission traverse around those parameters. Our distance traveled, which is not a requirement, but we do have a goal of around 20 kilometers. We might do more or less than that. Again, a function of the traverse. And then the traverse will be baselined along, of course, with the site selection at CDR. Super quick tour of the surface segment, which is our name for the rover with the instruments. You can see the blue text is showing those instruments that I made a really quick reference to along the bottom. Downward facing to the soil are the M-Solo instrument, which is a mass spectrometer, and then our near-infrared spectrometer, NERVIS, are both down there looking at the surface underneath the rover and any of the tailings that come up from the drill. You can see the top part of the drill poking out the top of the rover. And then our divining rod, if you will, is the neutron spectrometer system, which is something that we're looking at continuously while we're roving in order to be able to look at the neutron count changes as an indication of where there could be water ice and where we should ultimately drill. In the green text, you see various features of the rover, including an explicit steer mobility system, very different than what you're used to seeing with a 6-wheel rocker bogie of traditional Mars rovers. The way we move and where we are in a polar region very much drives the design in order to accomplish our mission. Solar arrays on the sides, which of course is because the sun doesn't get very high off the horizon when you're in a polar region. So you need to point to the sun, which would put it at nearly vertical angles along the sides of the rover. And then of course the radiators up on top, because nothing but the blackness of space up above. Then lots of situational awareness, cameras all over the place, as you can imagine, performing basically 2 primary functions. Navigation, of course, stereo imaging and so forth, all the way around, up on the mast, up on the top, but also hazard awareness, right? Cameras that are down located near the wheels. It's sometimes hard to see what's happening underneath you when you're using your nav cams to look out ahead. And so we have cameras down below. Quick overview of Viper in relation to other notable roving robotic missions. The top row there are familiar Mars rovers, and the bottom row are lunar vehicles. You can see how Viper compares. If we had more time, I would spend more time on some of the very interesting differences between Viper and those. Quick hits on a couple of them. It's a completely solar electric powered mission. You'll notice that plutonium and polonium are used quite extensively on the missions. There's reasons that we're not doing that. And then also we're a relatively fast rover. Relatively, maybe not in comparison to even a human walking, but in comparison to the rovers, we're pretty quick in being able to move around. This is being a fact. And then in a polar region, the lighting conditions, and that includes the shadows, move quite quickly. So the rover has to be able to move quite quickly too, to stay ahead of very dynamic. Now I'm going to move into some of the progress that we're making here in our development. This is a quick image of some of the lighting testing we've been doing at Ames, representing soil conditions, cratering, positive and negative relief conditions, solar lighting conditions, and helping the drivers understand what they might see through the lens of Viper's nav cams, but also understanding how to optimize some of the algorithms and stereo viz algorithms. This is a messy little picture. It's actually a clip from a video of a dust box test that we're doing of our rover release mechanism. And that's the rover release from the lander itself. We're going on a astrobotic lander through the CLIP vehicle, contracting, of course, lunar delivery means. And so this test here was just making sure that the rover release mechanism operated after what could be a very dirty landing. We're not quite sure, but we're taking a pretty aggressive stance on this through this test. We're also doing assembly pathfinder work. This is taking place at Johnson, and we've just completely refurbished a clean room out there. And this is some of the early practice work that we're doing. And you see in the aluminum there, just for this purpose of assembly pathfinder, this of course is not flight or even EDU hardware. We've built the lower frame, the belly pan, and some of the chassis parts for the rover. The red boxes, and there's blue boxes as well, are 3D prints of key components, and the team is already practicing assembling the rover. This is not the finished design, but it's getting the team used to operating in this environment, procedures writing, handling various pieces of equipment. For example, the image you're seeing now is of M Solo, a 3D print of M Solo. And just the whole activity of behaving with flight hardware and some of the peculiarities of how you have to insert, install, support humans holding, have hands here, but don't put hands there. So we're really getting quite serious very early in the flow on how we're going to build this to reduce risk later. This is a earlier RP-based, resource prospector-based rover that we've been using for extensive testing. This comes from a video clip as well, showing all the degree of freedom that the Viper rover has, quite a bit of articulation, which leads to both nominal and some off-nominal gates of movement. We haven't been down in these polar regions. We haven't been down in a PSR. And based on data from LCROSS, LRO, and other missions, it could be a very curious and challenging environment down there. We know it's going to be cold, but the exact nature of the soil, whether cemented and quite hard or downy and fluffy, is going to require us to have flexibility and capabilities out of our rover. So we're trying to design that in. We're also doing testing out at NASA Glenn at their slope facility. The top left corner there, you see a grill in the horizontal bed. That's the sink tank. We've spent a fair number of time down there and have forced ourselves to sink and then have pulled ourselves back out, which is quite remarkable for the history of the sink tank and bodes well going forward. This incline, 25-degree incline that you see the rover test bed on right now, of course, is beyond the requirements performance of the rover. We're intentionally trying to get it to slip as we're moving up this angle, up this slope. And what it's doing is helping us understand and calibrate our pose estimates and our slip prediction algorithms. There's a number of flight software activities that we're doing here in order to be able to operate the mission with as high a confidence as possible, while we're also calibrating with an outer loop using stereo visualization optic flow techniques. So really quite impressive. And we're testing it very early to make sure we understand the limitations and to tune things up. And here we have the rover going down a mock-up of the Astrobotic Griffin lander. They actually shipped a mock-up out to NASA Johnson where the rover is being built. And we were doing testing, going down their first iteration of rampways, as they call it. And we even, as you can see by the plywood blocks that are there, trying to cause some anomalies, right? We have a rampway that lands on a rock and twists the entire exit means. And so we've been doing testing with this as well, both with rigid suspension, meaning we're not doing active suspension. We just look like a rigid 4-bar system. And then also with a tuned suspension. So we're just really trying to get as smart as we can with the capabilities of the rover, both the highly capable and the more primitive, so that we have a very good familiarity when we actually find ourselves on the mission. Just thought I'd give a nod to COVID. The pandemic, of course, forced us to do a whole bunch from home. And so we've been teleworking like many of the rest of you. This is a driving simulation taking place at one of our training coordinators' office at home. And you can see on the left screen there, on that laptop is the driving tool, the commanding tool. On the right laptop, on the right side, you can see the situational awareness mapping and so forth of where we are driving, the locale. And in the center, you can see the NavCam images that are part of a very high fidelity simulation that we've got together. And then under the desk, you can see some feet warmers down. Final Viper mission status, we are on track to a late 2023 mission start, November, December. We're working through those service plans and scenarios now. Both our schedule and costs are tracking to plan, I'm pleased to say. We are holding multiple meetings with Astrobotic. As you can imagine, the level of integration and discussion that's required is incredible. We're working interfaces, loads, and requirements. The coupled loads analysis with SpaceX, the selected launch vehicle that we're going to be using, Falcon Heavy, are all being talked about and actively worked now. We're building design confidence through analog testing. You've now seen some still images of just that. This is just the very beginning of the physical interface testing with Astrobotic. Much more to come. We've delivered an entire wheel system up to them, up to their location in Pittsburgh, so that they could do testing there while we're simultaneously doing testing within NASA. We're also conjuring what we're calling last-ditch locomotion means should Viper get stuck. I say that acknowledging we haven't gotten stuck yet, but we're not reliant on that. So we're looking at different unconventional, but within the capabilities of the rover, ways that we could find ourselves getting out of a stuck situation. So that's both fun and important, trying to understand the best trades there. And then finally, as a lead in to Tony's talk, much site analysis and traverse testing trades are going on. And they're optimizing against the capabilities and constraints of the rover. As you heard, our CDR is coming up in October, which means the rover is done being designed at that point, and now you have to work with what you have, the rover that you ended up with. And so this is all part of that site analysis work, and the landing site selection will be revealed at the Viper CDR. And that's everything.
Great, great. Well, thank you so much, Dan. And we are all, again, so excited to have Viper, to be looking forward to Viper and all that it's going to reveal. And it's really going to be enabling for a sustainable future on the moon through identification of resources. So just fantastic. And if I could ask if you could stay around till the end, and we'll have a Q&A session. And I want to note that there's been quite an active Q&A going on in chat. Professor Elman has been answering a lot of questions about Trailblazers, so that's just great. So feel free to ask your questions in chat during the orals. So we actually have another talk on Viper right now. This is more of the science-focused talk, and is going to be given by the scientist, the lead scientist for Viper, Dr. Tony Colaprete. And Tony, in addition to his current duties, was also heavily involved in LCROSS as well as its project scientist. So Tony, take it away. Oh, Tony, are you there? You may be on mute.
I am on mute. I had to find the mute
there we
button.
go. Very good.
Thanks.
Okay.
Sorry. Yes. I'll talk about more of the science measurements and observations and the traverse plan that Viper is considering as we go forward. I'll not read each of these bullets here, but as this is recorded, you can come back and review at your leisure. Viper is about characterizing volatiles, including water, of course, really trying to understand their distribution. At very low concentrations, we want to measure down to at least 0.5%, but the instruments are capable of making observations much less than that, 0.1% or even less. The spectral range and mass range of the near-infrared spectrometer and mass spectrometer cover a wide range of key volatile species, everything from molecular hydrogen out to ammonia, methane, and of course, water. It is a mapping mission, and I think this is quite unique about Viper in that it is really at its core trying to understand the distribution and abundances of these volatiles in a statistically meaningful sense across both lateral and vertical scales. That's really important if you want to understand the resource potential of these volatiles. It's a page out of the USGS playbook, if you will, and we are adopting those techniques, geostatistical mapping, core sampling, etc. techniques to understand the distribution. It's also very much a science mission in that we have a litany of direct science objectives and hypotheses that we're going to test with the mission by making these various measurements here that I've listed. Now, I mentioned it's all about volatiles and mapping. Of course, understanding the context of which you make all these observations, it's critical. Bethany commented on this with regards to temperature. Temperature is key, we think, for volatiles at the poles. So we measure temperatures, but we also measure other things, including subsurface temperature, mineralogy, geomechanics, composition, etc. Because all these things we want to pull together into a better understanding, better predictive capability for understanding where volatiles, especially water, could be located. Here's the 4 instruments that, science instruments that we have on the rover. Really quickly, the neutron spectrometer, Dan mentioned, is our hydrogen nose out in front of the rover. We have the M-SOLO mass spectrometer, near-infrared volatile spectrometer system, and then the Trident drill. And this table captures some of the key observations each of these instruments make. NSS measures water equivalent hydrogen, measures hydrogen while roving down to a meter. This is key to get the adequate density of observations to make a good statistical prediction with a known confidence level. We need an instrument like this to constantly be observing subsurface hydrogen. NERVIS and M-SOLO are on continuously while driving too, and they tell us everything about the surface in terms of composition, temperature, high resolution imaging, and key isotopes while driving. Then finally, Trident samples down to 100 centimeters in 10 centimeter increments, brings up samples for both M-SOLO and NERVIS to sample. Whoops, I've got it on a timer, which is not what I wanted. Okay. And also what's important about Trident is it measures subsurface temperature in 2 locations. It's got 2 temperature sensors, one located at the bit, one above it by 20 centimeters. That's going to provide a wealth of confirmation data of the predictive models of thermal models that we have. Right now, we don't really have a lot of subsurface temperature measures, none at the poles. So that's going to be a really unique observation. I mentioned the instruments are on while driving. So we have really 2 modes of operation. There's prospecting and there's drilling, science operations, that is. This slide represents what's occurring during prospecting. We have the neutron spectrometer, the NERVIS system, and M-SOLO on continuously while roving or parked. And this little graphic just illustrates, what we're, as we're roving along, we're making these measurements all simultaneously. So again, it's exactly what Bethany was talking about, making simultaneous observations of temperature, hydration state, subsurface hydrogen while roving. Being able to pull all that data together continuously is critical. Is so much more powerful than if you just made individual observations one separate in time. While drilling, we have M-SOLO and the near-infrared spectrometer on, observing the cuttings pile, as Dan described, 10 centimeter bite at a time. And what we do is we bring up the cuttings, we brush them into a pile, we watch them for a number of minutes, 5 to 10 minutes, until everything's sublimed out of there. And then we go back down and we take another bite. At the bottom of every drill, we stop and pause to take a subsurface temperature measurement. What's really interesting about this observation, in my mind, amongst other things, is that we get to see both the water in its solid state. NERVIS is a reflectance spectrometer. It gets to observe whatever volatiles are there coming in as ices or adsorbed water. And then M-SOLO gets to see the volatiles as they come off and sublime. And that's really makes a great combination for, again, observing how are really constraining the state of volatiles in the subsurface. So where are we going? There's a number of constraints on this mission, being solar, direct earth communication, slopes, trafficability, roughness. It's this giant matrix of ands. So we'd be pretty much left with actually a small number of areas at the poles of the moon where all these constraints can be met. The good news is there are several areas, and they're shown here highlighted in yellow. These yellow areas are areas where we have locations with less than 70 hours of shadow over our mission period. So we call these safe havens. When the Earth sets and we can no longer communicate, we have to park the rover. We park in one of these safe havens where it has continuous sun, except for 70 or so hours, and it can easily survive on battery power. We awake the next day and continue the mission. And you can see in the background overlay is the Lunar Prospector hydrogen map or neutron flux map. And here's Cabeus, where L-Cross impacted right there. And the areas we're looking at in particular are the Haworth area, the Nobile area, and an area down here in Shoemaker. The insets here show what we call ice stability regions. So we divide up the areas where we think water could be stable as a function of depth and temperature into 4 zones: 1 surface, one shallow, one deep, and one dry. Dry meaning in the top, down to a meter deep. We expect temperatures to be too warm to ever have water ice. Stable, red being at the surface, like a permanently shadowed region. We expect water ice, the temperatures to be cold enough for water ice to be stable there. At each of these locations, we're building a range of traverses. We've been doing this for years now, and we get higher and higher fidelity each and every year, every cycle we do on this design. This shows just a general structure of the traverse plan. In each lunar day, here's each one of these yellow bars is a lunar day, a lunation. This leg is when we're active. Leg one is when we're active during the lunar day. And then this hibernation period is when the Earth has set and we have to part because we're a direct-to-Earth communication rover. In each leg, we have what we call rails driving and then science stations. Rails driving is how it sounds. You're on a rail, you're going as safely and as efficiently as you can to your next science station. All the instruments are on all the time, regardless. But here science is not in the decision loop. It's really just rover operators getting the rover to the science station. At the science station, which is represented here, we have a plan, a traverse plan within it, and various drill sites. Here, science is in the decision loop and actually guiding the rover and including location of drill sites. You're looking at real-time data. So it's a very integrated mission, integrated between science and operations, and it's a real-time mission, which is going to be is quite unique and going to be quite exciting. This is an example of a traverse. This is for the Nobile study site region. It's just an example, but a recent one with the most current rover capabilities. Real quick, this map here on the right shows an area near Nobile. These ice stability depths I mentioned before are shown here with this key in these colors. These three PSRs are key PSRs we're targeting in this area. They're fairly large and quite old based on the estimates the science team has given. This is about 500 or so meters across this permanently shadowed region. This little bullseye over here is where we have come down and landed. And the green lines show the rails driving to each of the science stations. These little circles indicate either a science station or some kind of activity like a recharge or a hibernation. These little gold circles or gold squares here are the safe haven locations. You can see we come to these safe havens, for example, here periodically to survive Earth down. This is a really fun traverse, in my opinion, because we get to visit all three of these PSR locations and make measurements all along the way. Some statistics on this particular mission. This one is fairly long. It's at least 4 lunations long. And we mapped out 106 days with 28 more total operational duration. The total traverse distance on this is 27.4 kilometers. So as Dan was saying, this is a pretty sporty little rover. We're going to do not quite 30 kilometers in 106 days, which is pretty great. And actually just 45 days of operation. The other days is when we're in hibernation. We have here in this plan 12 science stations, and this is the breakdown between them: 2 PSR, shallow, deep, and dry. And that's quite that's the minimum number. We certainly can probably add more to these. That covers a total map in the science stations only. We're mapping over or close to 4,700 meters squared of real estate and have 32 drill activities. So this is really going to provide a lot of data at very high resolution. Okay, let's go to the next slide. Real quick then, those plans that you saw were done on basically a data set that's a 20-meter resolution, including LOLA, DEMs, digital elevation maps, thermal maps, etc. We've been working very hard over the last year or two on high resolution data products, and this is an example of one. We have a shape from shading DEM, which is at 1 meter scale, made from LRO LROC NAC images. And then we use that DEM, 1 meter DEM, to calculate slopes, calm, sun, etc., but also temperatures. And this is a product that Matt Siegler, who's a co-an on the Viper Science team, has provided. And it shows really the unprecedented detail of thermal prediction that we're capable of having with thanks to NAC imagery and the awesome modeling that Matt and Dave Page can do. This is, if I jump up real quick, this is a zoom in of this PSR area right here. This is at 20 meters. So not bad resolution. This is what it looks like at 1 meter resolution. You can just see the structure is incredible at this scale. We knew this would happen. We plan at these scales now. And then you can see here we've drawn in this particular example. This is for a science operations sim that was conducted. We have a dry science station here, and then a deep and a shallow. And we go into each of these science stations and we plan them at this level. This is now zoomed in. Each of the pixels on this map is 1 meter. Each, you can see the little dots here. Those are what are called drive segments. In between each of these dots, the rover drives in a waypoint fashion, about 4.5 to 5 meters at a time. At each waypoint,
1 minute.
Thank you. This is like my last slide. Each of these points, the rover stops so we can take navigation images. And at the same time, we take a series of images from the Nervous imager, multicolor images there, et cetera. So all along these segments, we have every 5 meters a wealth of data coming in. Also at each of these points, we do a panorama to help with navigation. So one of the things we've done over the last year is really turn the rover camera suite into a science instrument. It was never meant to be, but it's critical data. We're working closely with the rover imaging team. All that data, rover imaging data, is going to go to the PDS, et cetera. So we're going to have a wealth of image data too, at really unprecedented coverage across these scales as well. And I will end there. I don't need preaching to the choir here. I don't need to really say how incredible the last decade and a half has been in terms of discoveries at the moon and rewriting textbooks, et cetera. Viper really will conduct a next level of exploration at the poles of the moon, getting down to the surface, having mobility of many kilometers, and looking both at the surface and subsurface in ways we haven't yet. Hopefully it will really feed forward to both exploration and science next steps leading into Artemis and beyond. And with that, I thank you. The last thing I will say actually is the last bullet there. We are really excited and looking forward to bringing on new science team co-investigators with the call out right now. So really looking forward to bolstering and improving the team. And that's it. Thank you.
Awesome. Thanks, Tony. And I can't wait. This is going to be such an enabling mission. And boy, what an exciting thing. And I want to continue to encourage everyone to ask questions in chat. That's been very active. I want to make one brief note that we're going to be taking a group photo after Donald James's talk. So if everyone could plan to be around, and those who are willing to turn your video on at that point. So at this point, I'd like to turn it over to my co-chair, Mahesh. Mahesh, please.
Thanks, Greg. Okay, so I realize that we are slightly behind schedule, so we'll swiftly move on. The next talk is going to be presented by my colleague from ESA, Dave Heather. And Dave, thank you for breaking your holidays and giving us an update on prospect payload activities. So over to you, you have 10 minutes.
Thank you. You can hear me okay?
Yeah, that's all very good.
I'm having problems sharing. It's saying I'm not allowed to share.
Maybe try again. Maybe it was going through transition from the previous speaker to you.
Yep, let me go back.
Still saying?
It's still saying the same thing. Can somebody else bring my slides up? I sent them onto the Dropbox.
Ricky, do you have Dave's presentation?
Dave, go ahead and try one more time. I made you a co-host. That should give you all the capabilities you need.
Okay. It's not letting me do it. Give me one. No, it's not letting me do it, I'm afraid. It says I don't have permissions.
Unfortunately, I do not have your slides right now.
So I can try quitting the Zoom and coming back online. I'm sorry for this, but
let me suggest something else, Dave. So while you sort it out, I wondered if Alexandra is online and he can give his presentation and we swap it around. Alexandra, are you ready?
Yeah, it's fine with me. I'm ready. We can swap.
That's great.
Sorry for the problems. Sorry.
No problem, Dave. See you in a bit.
Yeah.
All right. So we swapped those two presentations. So Alexandra is going to, I mean, you will recognize him from the picture that Dave Parker showed in his slide. So Alexandra, you are already a celebrity there, no pressure. So Alexandra is going to be talking about ESA's ISRU demonstration mission activities that are currently taking place. So Alexandra, you have 10 minutes.
Thank you. Can you see the right slide?
Yeah.
Okay. So
to the end. So we are now seeing your presentation mode. I think you need to swap your displays. Let's see if it works. Yeah, that's much better. There we go.
Thank you.
I'll start.
So I'm going to present you what we are doing at the moment at ESA regarding the definition of the science objective for our ISRU demonstration mission or ISRU DM. So the objective of this mission is going to the moon and trying to extract 50 to 100 grams of oxygen from the lunar minerals, so from the lunar regolith. We do that to first de-risk the technology that we need from basically across the whole chain, from getting the regolith from the surface, getting into a reactor, trying to pre-process it, process it, purifying the product, so the oxygen, and maybe store it. So there is a strong technology aspect, but on top of that, we of course want to definitely actually want to do some science with it and advance the science also across this whole chain, because we think at each step of the process there is science that can be done, and that would increase our understanding on how we can actually use lunar resources. We'll also learn about, at ESA, we learn about how actually we do payload operation at the lunar surface. And these 4 bullet points will help for the fifth one to prepare a future pilot plan. So as we scale up and get closer to application scale, we need to answer the first point. So that's the whole scope of the mission. It's currently planned around 26 to launch around 26, 27. It will be on board either the European Large Logistic Lander, which I think was presented by David Parker, or it will be on board a commercial lander. The payload is expected to be below 80 kilograms. And we are currently in a phase B1 challenge. So the phase B1 this time is separated in 2 steps. So we have a challenge where we have 4 consortia currently competing with different processes, and only one will actually work on the process for 12 months to get a full B1. So currently, the science requirement we have, we only have like 3 shards, 3 shields. It's really it's process independence. At this stage, we don't know which process we're going to use to extract the regolith. So I'm not going through the whole list, but as you may know, we have processes. You can use hydrogen, you can use methane, you can use molten salt, you can maybe melt the regolith. You have various way of extracting the oxygen from the regolith. But at this stage, we don't know exactly. We don't know yet which process we're going to use. We'll know in the end of August, when we do the selection to the next phase. So currently we only have this quite generic, let's say, scientific requirement where we want to know about the chemical species we're gonna extract in gas form. So maybe also all the volatiles we're gonna have from the regolith once we heat it up. So we have this range of mass of 50 AMU, for instance, on the concentration of 10 ppm. I'll come to that after. But we also want to know about the contaminants. So if we extract the oxygen as gas or liquid, we may have some extra contaminants that could come in a process. We need to understand that, of course, before scaling it up. Regarding the feedstock of the material we actually put in a reactor for the process, we need to understand the minerals. So yeah, we know what we put in a reactor. If we have pre-processing step, basically we need to follow what the concentration of oxygen at every step, or what are the minerals actually we beneficiate on the way. So this would be the core part of the, let's say, the first scientific requirement that we've defined. And then if we can go a bit further, we could even learn about the elemental composition. Depending on the process we choose, it might be actually more important. But also on the byproducts, since we'll end up with metal powder or partially reduced metallic, partially reduced regolith, so like still some oxide from the regolith, but maybe not as the original composition. So we need to understand that and measure that. And the electrical conductivity could give us some information regarding actually the potential reuse of the byproduct. So that's the first set of requirements we have defined. But now we want to actually go through the whole chain and try to add new requirements to better understand the science behind it. So when we're going to do regolith acquisition, is there some science to do regarding the way we're going to scoop, we're going to drill? Can we learn something about the surface, about the regolith properties, its composition? That's something we have to define. Then we're going to transport it, same, depending on the technology we're going to use, with maybe auger, maybe some vibration system, we don't know. But is there some science to learn at this step as well? Then we're going to get closer to actually the core of the mission. So when we're going to start pre-processing, so maybe we need to sieve the regolith, maybe we need to sinter it to get maybe some pellet or preform of regolith. For sintering, there is a lot of parameters. Sieving, we know, is very difficult to do on the moon. So maybe is there an experiment we could do or some science that can be done at this step so we can learn something to do better in the future. Then we get to the core of the process of processing. We need to understand better the scalability, the energy aspect of the process, as it has to be scalable, of course. All the science we do on ISRU at this stage is done on ground. So we need to understand better what's the delta to do it on the moon, and is gravity, the lunar environment strongly impacting our regolith oxygen extraction process. Then, depending on the process which is actually chosen, we will have peculiar question to answer. If it's, for instance, the molten salt electrolysis process, regarding salt losses, regarding current efficiency, parasite reaction, there'll be many science questions that could be answered, or some experiments that could be done with this payload at the lunar surface. Last but not least, once we have our oxygen, or if it's in the form of water, we need to, of course, purify this product and understand what are the impurity levels, what are the filtration needs, and if we have a byproduct, what it is it metal, and what can we do with it? So that would be the core of the mission. If we can extend it to, we have an optional extended mission, if we can have more mass or more time at the surface, but we could look into the product reusability, the product storage, or actually reusing the byproduct, so the metal powder, or partially reduced powder. So all at each step, we really want to define a new set of scientific requirements. But for that, we need the help of the whole, lunar science community. So the idea is after this phase B1 challenge phase, which ends in end of August, we will open a call to create this ISRU-DM research group. And members of this group, we hope will be scientists or technical experts from all Europe, and they will help us to define this new science objective across the whole chain. They will help us making decisions between maybe some science and technology trade-off. Maybe they will help us prioritizing some experiments. We want them to also highlight some knowledge gaps, maybe something we haven't considered, something we simply forgot. That's something we expect from this team. And of course, we want them to become the main users of the generated data. So this call is expected to happen, at the end of the year. So we are currently defining the terms of reference. So stay tuned, and we hope to receive many proposals to join the team. Thank you.
Great, thank you, Alexandra. You finished 2 minutes before your time, which is wonderful.
Okay, I thought I had 8 minutes.
Yes, no, you are right. But great, thank you. I think we will move on to the next one, but do stick around at the end to answer any questions. Dave, are you with us now?
I am, yes.
Good. So we have your presentation. Do you want us to share from our side?
I can try and share from my side again if you want.
Yeah, just do it once,
try
and if
that
it doesn't
first.
work, yeah.
Yeah. This is looking more promising. So
something is coming. Yeah, I can
Yep.
see your presentation.
Excellent.
There you
Thank
are.
you very
So,
much.
there you go.
Okay, thanks. And thanks to Alexandra for stepping in. I'm sorry for the problems. So I'm going to give a quick presentation today about the ESA Prospect payload, which is scheduled for launch on Lunar 27. I'm doing this, of course, on behalf of the full science and industrial team, although I'm the one speaking. There are many people working behind this, of course. For those who don't really know too much about Prospect, there are two primary components on Prospect. One is the PROCEED drill, and the other is the Prosper Analytical Laboratory. You can see those in the schematic shown on the bottom of the slide here. And the Prosper Laboratory itself is comprised of two smaller elements: the solid inlet system, which allows for the transfer of a sample into the laboratory, and then the analytical laboratory itself, which comprises of a number of spectrometers. In terms of objectives for Prospect, we are going to be performing a cryogenic extraction of lunar regolith from depths of down to approximately 1 meter. So we'll be sampling the subsurface and analyzing the regolith that we extract, trying to understand the abundance, the composition, and the distribution of any lunar volatiles which we find in the south polar region of the moon. The analytical lab itself comprises of a magnetic sector spectrometer and an ion trap mass spectrometer, a whole series of ovens that we will also be able to use to ramp up to higher temperatures, so as we can do some demonstrations of in situ resource utilization, so extracting oxygen from the lunar regolith as well. So I mentioned this is being developed for flight on board the Lunar 27 mission, which is scheduled for launch in 2025 and is part of an ESA and Roscosmos cooperation. We're now in phase C of this development, but we're also looking at some additional flight opportunities with some of our other international partners, such as NASA and JAXA. So this is a kind of a closer image of what the two major elements look at. The PROCEED drill element is being developed by Italian industry, by Leonardo. This will be capable of acquiring samples down to approximately 1 meter. It will acquire 2 samples, the larger of which will be given to the Russian instrumentation, and a smaller sample will be extracted that will pass on to Prosper, our own European laboratory. It's not just a drill. It will also have a multispectral imaging system built into it. And there'll be a permittivity sensor within the drill that will allow for remote detection of volatiles, and some temperature sensors within the drill as well. Once we've extracted the sample, it gets passed on to the Prosper laboratory, which is the development of which is being led by the Open University. Prosper will receive the samples. It will image the samples as well with a separate imager before sealing it in the ovens and heating them, and then passing them through the various spectrometers, which I've already mentioned. One slide just to highlight the development status of where we are with each of these major elements. For PROCEED, we had a successful demonstration of the full capabilities of the drill design at the end of 2019. So we were drilling into lunar simulant and extracting samples. We had some anorthositic inclusions within our drilling area as well, just to make sure that the drill was capable of passing through those. For Prosper, for the laboratory, all of the key elements are being tested individually and prototyped at the moment. So this includes the camera, the solid inlet system, and the spectrometers. And in general, we have a detailed design ongoing. As I said, we've just entered phase C. So the detailed design, which is ongoing, and we have dedicated testing of each of the components and the units. We're looking specifically, of course, at survival testing for extreme temperatures that we expect to encounter when we get to the moon. Also, environmental compatibility and the lifetime testing, making sure that we can survive the colder temperatures and hopefully survive overnight as well on the moon. And looking at the dust compatibility. We had some recent measurements, for example, from the science team of the camera, which was specifically looking at the dust compatibility and the dust coverage that we will be able to tolerate. You can see over on the right-hand side, which may be of interest here, some schematics of the drill itself. And you'll see that for the drill, once we get down to a certain depth, then the sampling tools will be deployed. The Russian sampling tool is the larger tool you can see on the right-hand side. And once we've reached the depth that we would like, then there is a very small push tube, which is deployed from the base of the drill that will extract the smaller sample to be passed onto the PROSPER analytical laboratory. One slide on some of the science support activities which we are covering at the moment. You'll see on the right-hand side a photograph which from Hannah Sargent, from some work that she completed last year. There's a link to the publication there as well for those who are interested in reading more. Hannah used this setup that you can see in the photograph to basically do a proof of concept, let's say, of the evolved gas analysis that we are hoping to use PROSPER to complete. So we used some hydrogen reduction to successfully demonstrate the capabilities of PROSPER for evolved gas analysis, and also to extract oxygen from the lunar simulants. So it's a proof of concept of the full capabilities of the PROSPER analytical laboratory in that respect. The results also showed that there was a very strong correspondence between the ilmenite content of the sample that was being tested and the oxygen that was the yield of oxygen that was extracted from the analysis. So ilmenite will be a key marker for us when we're doing our ISIU studies. In addition to that, we are continuing to work on thermal modeling throughout the complete sampling and drilling chain, because it's of course very important that we try to preserve as many volatiles as we possibly can from the sample through to the extraction and analysis. We are hoping to minimize the volatile loss to less than 35% if we can. And that will allow us to still take some feasible measurements and to look at the volatile content of the original sample. We're also looking at the magnitude and the impact of all of the potential contaminants within the full cycle of analysis. And we're looking at prioritizing the prospect operations, so trying to maximize the science return whilst we're minimizing the resources that we're using in terms of time and power and data. One final thing that we also need to bear in mind is we are a static lander. So where we land is very important, and the attitude that we land is also very important. So the attitude of the lander. So we are doing some work to characterize the landing site. This is extremely complex, of course, because of the topography and the complex illumination situation at the South Pole. So we're trying here to balance the science objectives with the operational constraints. We need to be somewhere which will allow us to have enough sunlight for power and communications, but will be dark enough for volatile preservation for us to try to maximize our chances of sampling volatiles. So this work is ongoing. We've done quite a lot of work, as you can see from the map on the left-hand side, looking at various models for volatile preservation of what we would expect to see in terms of volatiles in illumination, and the 8 candidate landing sites that we have with our Russian partners. What we need to do now is try to time resolve these with the expected landing time and the lifetime, let's say, of prospect on the lunar surface. This is being done in parallel to some work on the radiative environment and the complex lunar polar illumination conditions from Oxford University. They have developed a thermal model which we're weaving into the landing site characterization.
1 minute, Dave.
Yeah, my final slide. So basically where we are at the moment, Prospect is currently being prepared for flight on Lunar 27 in 2025. We're also actively pursuing some further opportunities for Prospect and associated hardware, one of which is, for example, the exospheric mass spectrometer, or EMS, which is going to fly on the NASA Astrobotic mission scheduled for launch early next year. And if you have any questions, then I'm very happy to take them at the end of the session.
Thank you very much, Dave. And once again, much appreciated that you gave us the talk despite being on holidays.
Not a problem at all.
Good. Okay. Please do stay around for a little while. So let's move on to the final talk of this plenary. And I'm very pleased to introduce my colleague, Chip Shearer. He will be giving us an update on the ANGSA program, the Apollo Next Generation Sample Analysis. So Chip, are you ready?
Yes, I am.
Okay, I'll start the timer and I'll tell you when 2 minutes are left.
Make sure I can upload this to the screen.
Yeah. Something is appearing. Yeah, good. Are you ready?
Great. Well, thank you for inviting me to give this presentation. What I'd like to do today is brief you on ANGSA sample analysis activities, technology developments associated with ANGSA, and the lesson learned activities that we are doing within the concept of ANGSA that will provide us with additional insights on lunar surface activities. For many of you that don't know, ANGSA, the Apollo Next Generation Sample Analysis Initiative, was set up, was initially conceived and organized as a low-cost sample return mission. And within that context, it is examining what I call new Apollo samples that were Apollo samples that were never opened and perhaps even uniquely curated and uniquely stored, and taking the sample data and placing it within the context of 50 years of post-Apollo science and utilizing new analysis tools. The ANGSA targets, sample targets, are illustrated here. They include a double drive tube that represents sample 73001 and 73002, which were collected at Station 3 on this light mantle deposit shown here within the Taurus Littoral Valley, which is a landslide deposit, or the youngest landslide deposit coming off the South Massif. In addition to the 73001, which still resides within the core sample vacuum container that was sealed on the moon, there's also 73002, which is the upper part of the double drive tube, which we are currently working on and processing. In addition to those two core samples, there also is a suite of frozen samples that are shown, their locations are shown in blue within this diagram of Taurus Littoral Valley. And these samples were frozen upon their return to Earth and have remained frozen for the last 50 years. As I mentioned, the team is organized as a sample return team. And this diagram here just illustrates some of the PIs from the 9 research consortia selected and a variety of the other team members by their institution. And there's approximately 60 to 65 scientists and engineers involved in this initiative. What I'd like to do now is just illustrate at least some of the new data that we've been able to generate and focus on 3 areas. One, focus upon stratigraphy from the double drive tube. Second, on new and unusual lithic fragments and rock types that were sampled within this core. And then finally, some analyses of stable isotopes that represent processing or processes involving volatile elements. Some of the first data that were derived from the 73002, we're doing the preliminary examination activities. The processing of the core from pass 1, shown to your far left, illustrates grain size analysis. Those samples that were less than 1 millimeter versus those materials that were greater than 1 millimeter. Also, as you just saw, we also did X-ray computed tomography on this core, which again illustrates a lot of stratigraphy. More recently, Dick Morris at the Johnson Space Center conducted spectral and size fraction stratigraphy down this portion of the double drive tube. Paul Lucy and Son conducted multispectral analyses. This was a analyses done in situ versus the analysis that Dick did, which were primarily pulling out the individual samples and making those measurements. And this is just a optical maturity parameter that they were able to determine down the core. This second chart just illustrates some additional stratigraphic measurements within this core. Again, Sun and Lucy, using their multispectral analysis, were able to determine the iron and titanium concentration within the core, shown on the 2 diagrams to your left. The group at Washington University, St. Louis, and the University of Notre Dame were allocated individual samples from 0.5 centimeter segments along the core, where they accomplished major and trace element analyses. And this just illustrates the variation in FEO within the core. And finally, what I'm showing here is some work done at UNM by one of our students, Michael Cato, who is looking at the mineralogy of, I think, 7 or 8 different size fractions from the core. And this diagram here just shows the percentage of agglutinates on the samples from the 90 to 150 micron grain size fraction that he's analyzed. I was expecting all the way up to last night to be able to show you some cosmogenic radionuclei measurements, primarily the aluminum-26, which will give us a clue to the age of this particular landslide deposit. But Keyes Walton told me that they're still counting the individual samples. As I alluded to, there are a variety of new lithologies that we've been able to uncover within this core. Some of them are illustrated here in 2 different fashions. The diagrams to the left just are XCT images of some fairly unusual, unique lithologies that we found. And again, these are lithologies and rock fragments a little greater than 3 millimeters. And to the right are some BSE images and X-ray maps of, again, some rather unique lithologies that were identified and analyzed by SEM and electron microprobe analysis.
Chip, 2 minutes.
Okay. We have also been conducting a wide range of stable isotope analyses at University of New Mexico, oxygen, hydrogen, and chlorine. And we've essentially found that these isotopic systematics provide you with processes under which volatiles are being acted upon in the regolith, and also individual fingerprints of their sources, such as the DDH measurements and the chlorine isotopes. Finally, what I'd like to do is touch upon some of the work we've done in processing the core sample vacuum container. This is a container that the lower part of the core is in. The ESA contribution to this, which is past the design stage and in the fabrication stage, is illustrated in the bottom left. The manifold that this is connected to that essentially extracts the gas and samples it, is shown on the right. And this was essentially designed and built by Washington University, St. Louis, and delivered at the Johnson Space Center. Let me just quickly show you how the piercing tool is assembled, and the core sample vacuum container is shown in red. And this just essentially illustrates how this is assembled, and the base of the core sample vacuum container is pierced. Finally, on my next slide, what I just like to do is just illustrate some of the activities that we anticipate for ANCSA in 2021, 2022. We are organizing the Apollo 17 ANCSA workshop at the LPI at the second half of 2022. An announcement will be released this August. And this is the focus upon, or is in celebration of Apollo 17 anniversary, 50th anniversary, and the ending of all the great science that was done by the Apollo program. Also, we will have the first opening of a specially collected core sample container in the summer, fall of this year. This is really a completion of the first experiments to sample endogenous gases released from the lunar interior, which was a science goal of Apollo. This will also be the first examination of stratigraphy of a lunar landslide deposit, which is ongoing. And this summer and into the fall will be the first examination of Apollo samples frozen for almost 50 years. Thank you very much.
Thank you, Chip. Wonderful. Thank you. And I think that's the end of the plenary session. I can see that there are 2 questions in the chat box that have not yet been addressed. And I think those 2 are addressed to Dave Heather. Dave, are you still with us?
I am, yes.
So there are 2 questions that relate to Prospect. I wondered if you just wanted to make some brief comments on those.
Yeah, I'm just looking at them now.
Okay. There is one about the PRISM call, and it says Prospect payload is mentioned in the AO, but it was not mentioned in your talk. Do you want to say something about that?
That was simply because of lack of time. So yes, it has been selected for Eclipse as Eclipse payload for 2024. And I simply didn't mention it in the slides because it was a very recent announcement and I didn't really have enough time to cover it in detail, that's all.
That's great, thank you. And the second question is about a multispectral imager, which is being included with PROSPER. And the question is, what is the team hoping to measure, achieve with it?
The imaging will be, the multispectral imager will be on the drill. So we will be basically looking at some basic mineralogy. We'll have coverage that will allow us to look for things such as iron content, glass content, that sort of thing. But we will also be using the camera to look for grain sizes, look at the drill pile as it develops, as the drill descends. So basically giving us a rough indication as to the sort of regolith that we're looking through. So it's not a detailed composition, but it gives us a rough idea.
Great, thank you. And thank you to all those presenters who have been answering the questions that have been put to them in the chat box. Yeah, no, I think it's also great that everybody is thanking the presenters. So I'm very mindful that we are about 10 minutes, already 10 minutes over time, and we have entered a break. So I propose that I hand things over to Greg, who is going to chair the next session, and also he will then make an announcement what we do next. So Greg, over to you.
Great. Thanks, Mahesh. And thanks to all of our presenters. What an amazing session. I mean, I was thinking during some of your talks that when I started with NLSI 13, years ago, we were planning for this lunar future, and now it's upon us. We've had, of course, over a decade of successful operations with LRO, but we have Lunar Trailblazer, we have some of the others, Viper, et cetera, that we've talked about, and they are just about here. And things are about to change, and they're about to just get absolutely fantastic. So what an exciting time this is. And Mahesh, thank you for co-chairing this this session and co-chairing the conference in its entirety. You'll be seeing more of both of us as things progress during the week. I also want to say thank you to our sign language interpreter and interpreters, I should say. And I want to thank Ricky Guest for his expert operations of the conference so far. So I'd like to introduce our next speaker, and I mentioned at the beginning that equity, diversity, inclusion, accessibility is something that is absolutely important. And quite honestly, I would say it's as important as anything else that we're doing in this community, certainly in my institute, but arguably in the entire community. Being open, bringing in people who haven't had a chance to participate is extremely important, and I can envision a much better future because of some of the actions that we're starting to take. So, and because of that, we have several plenary speakers, and the first one is a very dear friend of mine for many, many years, Donald James. Donald had a 35-year NASA career. He started as a presidential management intern at Goddard, transferred to Ames in 1984. He and I were both in the Senior Executive Service Career Development Program, the same cohort back in 2004. He was selected to be the Associate Administrator for Education for NASA in 2014. And he retired from NASA in 2017. He's now a published author. His book is Manners Will Take You Where Brains and Money Won't, Wisdom from Mama and 35 Years at NASA. And his talk is going to be on diversity, equity, inclusion, and anti-racism at NASA. So Donald, please take it away.
Thank you very much. Just a quick sound check. Everything sounds good?
Yeah.
Okay, great. Thank you very much. I'm going to put up my slide. I just have two. Sure. Okay, so you should be seeing the main slide there. So Greg, I really applaud your leadership on this important topic and bringing it to the forefront of this forum. And I really appreciate all the participants who are thinking about these important matters. As I listened to some of the previous presenters, the one thing I know is the common denominator about everything that we have done on the moon, we are going to do on the moon and other planetary bodies, is that it involves human beings that have to work together, and human beings that have to be included. And so I'm approaching our topic today through the lens of my deep curiosity, interest, and experience in the topic of manners. And my brief remarks are based on the recent book that I just published that Greg mentioned. So with my younger brother, Dennis, you can see here in the cockpit with my superimposed book between us. My younger brother, my collaborator, is a captain with American Airlines. He's, as we speak, being trained to fly in the 787s. And both of us had long early interest in aerospace, and as well as inspiring students to get interested in the field. And so we wrote this book for students and early career professionals to share our thoughts on what we thought it takes to have a meaningful and fulfilling career. And it's an integration of my NASA experience and all the training I've had both inside and outside of NASA, as well as the wisdom that I learned from our mother. And I have concluded, especially with respect to inclusion, and that is the piece of this that I'm going to focus on, is that our manners are a highly influential variable in causing others to be and to feel included. And I'm using the word others deliberately to underscore the challenge we face in authentically connecting with people who are not in our, as the saying goes, our tribe. Inclusion really is a manners matter. So my definition of matter starts with the outward expression of our way of thinking and being. Our manner is what and how we do, say, express, or convey something. Our manner is the outcome of our experiences, beliefs, culture, opinions, or convictions, and it includes verbal and nonverbal communications. So manners is not just what is commonly thought of as etiquette or politeness, you know, the please and thank you stuff. And there's a place for that. And I believe pleasantries, civility, and respectful behavior is important if it is authentic. At this point, I'm going to ask you to try on what I call a pink suit. It happens to be the title of chapter 4 in the book. And pink suits are a metaphor, and they are meant to encourage trying something on that you might not otherwise try. And this is where you may be uncomfortable or feeling self-conscious if you wear the proverbial suit. And the pink suit I'm asking you to try on today is this. For organizations to improve their I or their inclusion, I submit that people in the organization must work on their manners. This is my hypothesis. And this hypothesis comes from my 35 years at NASA, all the training I've had, and things, as I said, that I learned from my mother. And it also comes from my wearing a lot of metaphorical pink suits. Let me share a quick story to illustrate my point. And I'm going to deliberately use non-gender specific pronouns here. I've taken liberties with some of the facts to clarify the messages, but the story is true. I had a colleague who by most accounts was a solid engineer. As part of their professional development, they accepted an opportunity to direct a program for college level students and early career professionals from multiple countries. A diverse group of mostly non-American young professionals, many who had worked the same program for years, was responsible for day-to-day operations. Unfortunately, my colleague didn't work out very well. There was something about their manner that rubbed the organization's staff the wrong way, and I was dispatched to the program's location to see if I could help. When I interviewed several of the staff, one message I heard clearly stood out. They said the NASA person did not listen. The staff also complained that the person presented rather arrogantly. And one person literally said to me, you know, Donald, I just do not feel included. It is as if my experience and views don't matter. Later, I spoke to my colleague about this. They were eager to deluge me with their complaints about them and their attitudes and work ethic. And they included references to their nationality as if that explained part of the problem. These people, they complained, don't get what I'm doing or respect that I'm in charge. After my colleague went on for a while, I stopped them and asked this question. Well, with respect to the program and what you want to accomplish, is it more important for you to be right about your views or to be successful? To my surprise, my colleague quickly replied, well, I know I'm right, and they just don't get it. My colleague, as smart as they were, had a manners problem. So my message is this, and this is what I tell students and early career professionals all the time. Being smart isn't good enough to be successful. Just like manners is not simply politeness and etiquette, inclusion is not simply adding to the invite list with a diverse cohort for good optics. When you include, as I see it, you are first and foremost engaging what I call presence listening. It's a listening that goes just beyond the well-understood practice of active listening, you know, where you train yourself to hear someone and then paraphrase back to them their point. If the speaker says, I feel heard, then active listening has been successful. Presence listening asks us to go a bit deeper, to go beyond the words that are spoken or perhaps not spoken. presence listening is searching for something that may not be obvious or readily communicated. Presence listening is empathy, where you seek to truly see and sometimes experience the world as others do. Now, if we were all like Mr. Spock with Vulcan mind meld powers, our task would be easy. Since we don't have those powers, presence listening gets us closer to capturing the signals we receive from others, including what they say, to get who they are and where they are coming from. And most importantly, what they could bring to the table or the project or the science mission. Perhaps it's a pink suit. So as I see it, a healthy functional work environment is one in which inclusion is the proactive manner in which one engages others. We approach our desire to understand colleagues the same way we approach a science investigation. We have great questions, we have rapt curiosity, tenacious investigation, and a commitment to let the data drive our understanding and conclusions. And the aha moments here can be life-changing. As I see it, of all the letters in DE&I, diversity, equity, and inclusion, as important as critical as diversity and equity are, if you don't get your I right, if we don't work on our manners, then we will likely place our success on the sacrificial altar of our righteousness, our ignorance, or indifference. Successful exploration for good of humanity really requires that we include. So I appreciate being included in this conversation. I know it's different than a lot of others, but if we get this right, our exploration is going to be outstanding. And so, Greg, once again, my friend, thank you for the privilege to be included in this.
Thank you so much, Donald. What an inspiring talk. And I can tell everyone online, having been your friend, Donald, for 30 years, maybe something on that order, that you practice what you preach. You have always been someone who listens as well or better than anyone I know, and what a great framework to approach this problem. You know, to treat everyone as humans, to be kind, and like you say so well, to listen. I love your Star Trek reference, and I'm reminded of, I think, twice when Nichelle Nichols visited Ames, and you know, she is the same kind of person. She felt very present, and just a absolutely wonderful person who helped NASA beyond inspiring people like another friend of mine, Mae Jemison. So anyway, thank you so much. And I'd like to open this to questions. If anyone has anything for Donald or relevant comments. Getting a lot of positive feedback in chat, and I've gotten a bunch of texts as well. So we have a question from one of the Science Organizing Committee co-chairs, Parvati Prem. Mr. James, thank you so much for a great talk. Could you comment on the role that power dynamics play in manners? Parentheses, e.g., I feel that sometimes the expectations we have for manners from those with less power are different, not always in a way that's fair.
Thank you for the question. And you're absolutely correct. The power differentials that you see in organizations are always really internalized by both the people who have the power and perceived power and those that don't. And so I believe it's incumbent upon those of us, and I learned this when I became Associate Administrator for Education, and I didn't always, I know that I didn't always execute well, or I wrote this book for myself to remind myself of what's important. That to be empathetic and to establish rapport with people from all parts of the organization and engage them and include them deeply is very, very important. When you're on the other end, I think about my mom had a set of rules and I put them in the book. And, rule number 2 is what other people think of you is none of your business. I really have to remind myself of that sometimes when I get concerned about, what people might think about me and all of that. And so it's really a call for each individual to step up what I call their manners game, manners really broadly speaking, and power dynamics and those labels that you're talking about absolutely are a part of that. That's why I wanted to focus on these issues. But yeah, it's a great question. And I think as an individual, my suggestion is, this is what I tell a lot of parents, please just be a role model and work on your own manners. Don't just hand a book to your kids and say, here, read this. You might need this sometimes. They probably aren't going to do it. And it might not work for a boss or somebody who's playing those games, but how you respond to that is a manners matter. And so I would suggest that you keep cultivating your ability to respond to that in a way where you're not taking it personally and what they think about you doesn't really matter anymore. That would be my first one.
That being said, I do recommend reading this book to everyone, though. So it's excellent. So there's another question. We might have time for 1 or 2 more, but this one's from Jay Greer. How do we track or evaluate that we are succeeding with positive outcomes from changing manners?
Well, for me personally, it's probably going to happen long after I'm gone, because my metric is that an early career professional upon her retirement at their retirement party will say, one of the things that really changed my life was reading this book. And so I hope that's the case, right? Or maybe they don't even have to point to it, but as long as they found a way to navigate their way forward by cultivating this, I would be happy. I don't, this work is not a work of scholarship. I want to just acknowledge that. This is just my experiences and my views and my training. I haven't thought about, I just want to instigate a manners renaissance, and I hope that it evolves. And over time, perhaps the way we interact with each other and how we view, quote unquote, the others and our civility, people will just sense that it gets better. But I think it's going to be glacial, but I'm willing to do my part.
Yeah, and already are in a big way, I would add.
Thank you, Joe. Thank you.
We have time for perhaps, let's see, here's one from Elizabeth Fisher. Hi, Donald. I know that a common tactic for trying to protect individuals, at least in grad school, from bosses who aren't understanding, is to try and diffuse the power. Do you think that this is an effective strategy for mitigating the influence of the person with bad manners? Thanks.
I'm not sure. This is not easy stuff. Somewhere in the book I talk about, and I hate to use the term red lines because it's kind of gotten politicized, but when I'm engaging with somebody, if I feel that my personal red line has been crossed in any manner, then I'm going to speak up and say something. But it's a calculus that I have to make in terms of what might happen. I know a senior NASA executive that was called the N word, and he chose to physically respond to the person, and that person the person who hit the other person lost his job. His calculus was it didn't matter, the person crossed the red line. I'm not sure what I would do in a similar circumstance, and so I'm a believer in role modeling and showing how you would exemplify great manners to the point where others want to emulate you. But at the same time, if you're in a situation where your personal space or your boundaries have been crossed, I absolutely believe you have to be willing to risk something to say that's not okay. And I think there's a right way and a wrong way to do that. But it's hard. I get it. And I appreciate the question. And if you learn tricks to this, please let me know.
I might like to add to Elizabeth's question that there are those of us who can serve as your ally who might be in different organizations, who might be at a equivalent power level to your boss, and feel free to contact us. I've made this offer to others. I'm sure, Donald, that you have done that as well.
Yeah, I can't say enough about that. Cultivating your allies, I call them intelligence operatives in the agency. By the time I got to NASA headquarters, they were all over the place, and I would go to them. And what they served for me was a read about the culture in the organization. Even though I'd been with the agency for a long time, I never worked at NASA headquarters. So the very first thing I did my first day in the job is I went to my friend Dwayne and I said, Dwayne, what do I have to do to stay out of the doghouse here? And he knew exactly what I was talking about. So I trusted somebody to say, okay, here's what I would suggest. Here are the people to talk to. And I went and talked to every person that he suggested. So by the time something quote unquote bad happens, and if you read the book, something really bad did happen to me, I felt confident that the people who knew me well and really understood my manner felt that they can support me and be an ally. And so I think that is critical. You have to do that work first before you really need it. Thanks, Fred. Great point. Great ad.
Excellent, excellent. And I see a comment from Carolyn along very much the same line. Allies are critical. That's for sure. We of like minds need to stick together, especially in tough times.
That's right. That's right.
Well, I'm not seeing any more questions. So Donald, thank you so much for just a really wonderful perspective, and one that I'm certainly going to carry with me, and I know a lot of us will as well. So really appreciate this talk, and I want to let everyone know again that there will be other EDI focused talks in a couple of days, and so I look forward to those as well. But thank you so much for drawing upon your 35 years with NASA and your new literary career, and we'll post an address for Donald's book as well. So
yeah, just put in the chat my email address. Anybody, please feel free to reach out to me and contact me or go through the website. I'm happy to talk to anybody. So
great. Okay, thank you, my friend.
Great to see you, Christina. All my friends. I appreciate it.
All right. You're always welcome. Yeah. So this draws to a conclusion, the first part of the forum, and I've really enjoyed all these talks again, and so what we're going to do now is do a group photo, which Ricky will capably orchestrate, and then I'm going to turn things over to Christina Gibbs. So Ricky, please take it away.
Okay, great. So everybody turn on your cameras. I'm going to give you a few moments to do that while I get things set up here on my end. We have about 200 people on, so I'll be taking probably 4 pictures. Once we get all set, have your cameras on, or at least a picture of you. Everyone is looking fabulous as I look through this list. And I am ready to go. I will let you know just before I take the screen grab, and then I will then move to the next page. For each person, you'll be on a different page, so hold your poses when I ask you, so that I'm not sure which page you're going to be on when I take that picture. So everybody smile. I'm going to get the first one going here. 1, 2, and 3. Perfect. Oh, you guys are all looking great. I'm going to move on to the next page, and here we go. 1, 2, 3. That's good. Now the people on the third page. I want you all to smile. 1, 2, 3. John Rask, you look handsome as usual. And on my 4th page, we've got a few people here. Everybody smiling. 1, 2, 3. And then now I'm ready for my last page of people who are all looking great. 1, 2, 3. Okay, great. Thank you. We have successfully taken that group photo. We might do another one at the end of the week to see if there's anybody that didn't get in the first group. So at this point, I will hand it back over.
Great, great. Thank you so much, Ricky. And we will be publishing these so everyone will get a copy. So I'd like to turn things over to my extremely capable deputy, Christina Gibbs, at this point. She's going to be talking about the poster session and introducing the lightning talk speakers. Christina.
Thanks, Greg, and hello to everybody. We have just a few more minutes and then we'll break for a break and poster session. But this year, as in all of our years, we're continuing with the student poster competition. We have 32 students competing this year, which is almost triple what we had last year, which is just fabulous. I want to thank the 20+ judges that volunteered to help us this year. There's lots of good work for them to score. So each student that is competing will be giving a lightning talk. And it was this year, the SOC suggested that we have the students talk in the session related to their topic so that they are introducing themselves and their work to the focused research community. That works with exception for 3 students whose posters are in the poster session number 1 and haven't had a session or a parallel session that they could present in yet. So we are going to have them do their lightning talks in just a minute. But for all the remaining parallel sessions and lightning talks, please do go to the session in the program online. You'll see the lightning symbol next to it, so you'll know that that's a student giving their lightning talk. I want to take one more minute and explain that we do have a poster sign-up sheet. We sent the link out maybe once or twice, and it's not required to sign up for a poster, but we really want to encourage distribution of attendance to different posters, and we want to make sure that the students as well are being seen and heard and have an opportunity to share, not just the students in the competition. There are students that are not competing, and they're in the spreadsheet highlighted in a lavender color. So there's the poster session today, but there's also poster sessions on the next 2 days. And so you still have time to sign up for those and do that. Next, I want to thank our ASL translators, our interpreters. This has been fabulous and something new that we're doing for the first plenary today and the closing plenary on Friday. And so I think this has been a really great addition, and we'd love to hear your feedback as well as the community. And so almost finally, I want to thank the LSIC organization. At their meetings, they used GatherTown, which is where I was exposed to it. And I hope you all enjoyed as much as I did. As Greg mentioned earlier, I asked to give it a try. And I really want to thank Ashkan Najad and Maria Luis for our team who put together our virtual conference room that you guys will see here in just a few minutes. They had a quick turnaround and learning curve, and I think it's come together really nicely. And I have not found the Easter eggs yet. I have to spend a little time looking for them. So with that, I am going to ask that Nicholas, we're just going to do this. Each presenter has 2 minutes to give their lightning talk, and that kind of includes the handover. So we want them to introduce themselves, their work, their poster title. They can have 1 slide and encourage you to come see them at their poster session. So with that, Nicholas is up first.
All right, can you see my slide?
We can, and I can hear you well. Thank you.
All right. So hi, everyone. My name is Nick Piskarich. I'm a first-year PhD student working at the University of Central Florida under Dr. Carrie Donaldson-Hanna. Again, as she mentioned, you can come see my poster today at 12:45 Eastern or 9:45 Pacific time. In our study, we investigated the compositions of the 4 largest irregular Mare patches and their surrounding regions using reflectance data from the Moon Mineralogy Mapper. Irregular Mare patches are hypothesized volcanic features that show 2 distinct morphologies and topographies. Constraining the formation mechanisms and origin scenarios of IMPs can give us insight into the timing and cessation of lunar volcanism. And IMPs could also represent ideal sites for future sample returns or commercial lander missions. So we analyzed the 4 largest IMPs, Sosogenes, Ina, Cauchy 5, and Mascaline. And moving forward, we intend to study mesoscale and smaller scale IMPs and use thermal infrared measurements from the Diviner Lunar Radiometer. So again, if you have any time, I'm in the Geology and Geophysics session today at 12:45 Eastern or 9:45 a.m. Pacific Standard Time. I look forward to seeing you there.
Thank you very much. Excellent. Aisha, you're next. Are you with us?
Yes, I'm here. Can you hear me okay?
I can. Thank you very much.
I will share my PowerPoint. Please let me know you can see it okay.
Yes, we can. Go for it.
I'll get started. So hi, everyone. My name is Aisha Khatib. I'm a graduate student at the University of Maryland, College Park in the Department of Geology, and I'm presenting work on classifying deep moon quakes using convolutional neural nets with my advisor, Dr. Nick Schmer and Dr. Ved Lekage in the department. The project focuses on deep moon quakes, which are these repeated periodic lunar seismic events that occur at focal depths between 800 and 1200 kilometers. They make up over half of the events in the Lunar Seismic Catalog, and they provide a lot of information about the lunar interior. The work that I'm presenting today focuses on 2 of the biggest subsets of these deep moon quakes, so A1 and A8, and provides to see if a convolutional neural net can be trained to differentiate between them. And this is the first step in kind of applying deep learning techniques to the existing inventory of lunar seismic events, as well as the seismic record taken by the Apollo network, to reanalyze and potentially add to these records of deep moon quake events. My poster is poster number 9 in poster session 1, Geology and Geophysics. And I hope to see people there, and I look forward to a great discussion. Thank you so much.
Okay, wonderful. And our last one for this portion is Lyndon Wake. I'm gonna maybe not say that just quite right.
Share my screen.
Wonderful. Thank you. Go ahead. Well, we see you. We don't see your screen just yet.
All right, good morning, afternoon, or evening, everyone. I'm Lyndon Wyke, a rising second-year geology graduate student at the University of Maryland. I work with my advisor, Dr. Nick Schmer, also Aisha's advisor, on identifying seismic methods of locating subsurface void spaces. These void spaces can take the form of caves, fractures, and lava tubes, and along with the rest of the Geodes, Tubes, and Voids theme group, we hope to utilize them as shelter for future manned missions to the Moon and Mars. My research combines computational modeling and in situ fieldwork of terrestrial analogs, and our poster, Detection of Subsurface Voids using GMesh and SpecFem2D with applications to lunar and Martian lava tubes, highlights the results of the computational component. We use GMesh to create a model subsurface containing a lava tube of varying size and shape as our void, and then we simulated the seismic wave field through this space using SpecFem2D. The figures below provide a sneak peek of our model spaces and resultant seismic velocity amplitude spectra between my abstract and poster, where my poster got much more accurate in spacing. And then you can see in these pictures that each tube creates a sort of characteristic hyperbolic signal that indicates a tube. I will be available to discuss my project further during poster session 1 today from 9:45 a.m. to 11:15 a.m. Pacific time. Thank you, and I hope to see you there.
Wonderful, excellent presentations, right on time and really informative. Thank you to all three of you. That was really good. And so with that, I would like to point out that Carolyn Vanderborgert put both the sign up sheet link for the poster session and the link to GatherTown in the chat. So thank you for doing that. And we can all take a few minutes break and head over to GatherTown. And Abby did mention we have a help desk. So if you find yourself needing a little bit of assistance, a lot of our team members, if not all of us, will be in the help desk to help get you started and oriented for especially this first poster session. So thank you. And we will see you again a little later in the post or in the parallel sessions. All right.
I didn't know I could get help trying to. Yes, I sent an email about it, but I never got the response, so I didn't know if it got passed.
Hello, everybody. We're at about 5 more minutes until we start the next session. And this will be the polar exploration session.
Hey, Ricky, I'm first up. It's Jim Head. Can I look at screen share?
Okay, Jim, you can go ahead and pull up your slide.
Okay.
And start your camera if you'd like, or give that a test.
Does that look good?
Your slides are looking good, full screen.
Okay.
And your camera looks good.
Okay. Thanks. How you doing, Hannes?
Holding up, pushing through, as we all. Nice to see you, if only in 2D.
Well, Noah, Petro, and Jim Head, good to see you guys.
How you doing?
Hello, Dave. Nice to meet you. Hey, Jim. Gang's all here.
Hey.
Yeah, if we were in an actual meeting room, you know, I'd be leaning over saying something to you, Jim, at this point, but I feel weird about doing that here virtually in front of everybody.
I can't wait to see you in 3D.
We could make
No, yeah, I think you can. There's a value added for not actually having to, you know, to see this in person. So you're winning there.
We could create a breakout room just for that eminent first row that always sits in the very front of each session room. Yeah.
I find myself getting closer and closer to the front as time goes on, just so I can see.
No, you can't start the time yet.
Oh, no. You got 58 seconds, Jim. No, I'm kidding. Just actually trying to remember, okay, we can do virtual filter backgrounds and all this fun stuff. So
yeah.
May or may not try that, but whatever works. Shall we get started, Hannes?
Yeah, sure. We can get started. Welcome to the Polar session. And we have a whole bunch of really interesting talks lined up for you. I'm one of your chairs. I'm Hannes Bernhard, postdoctoral research associate at the Arizona State University, working for the LROC team, and Noah Pedro.
Yeah, Noah Petro at NASA Goddard. And we're thrilled to have you here. Just as a reminder, we're gonna be trying to keep everybody on time. The formal presentations will be 8 minutes of presentation, 2 minutes of questions. One of us will try to get a timer on our screen, just as a visual cue for the presenters.
We'll give you a reminder at 6 minutes and 8 minutes. And then at the end of the session, we have 2 lightning talks of 2 minutes each. And then we'll have a little bit of time at the end of the session for discussions, Q&A, and of course, make ample use of the chat window for questions. Put a little Q in brackets to highlight that it's a question. And if you have a comment, just don't type it in. I'm kidding. If you have a comment, please share that with the rest of the community here. Please respect the intellectual property rights of each of the presenters. We don't want to, share screen captures or things without permission. And the presenters can close the chat window so you don't get distracted by the flood of praise for your presentations as it goes along. I'll turn the moderation over to Hannes.
I will replace my video with aforementioned countdown, which will change color as a visual cue, and you can pin my video screen if you like to always see the counter. So our first talk is going to be given by Jim Head and colleagues, and the title will be Geologic Context for Lunar South Circumpolar Region Exploration Implications for Goals, Site Selections, and Operation Strategy. Take it away, Jim.
Okay, thank you very much, Hannes and Noah. This is an incredibly exciting session because we're really taking a look at some of the broader aspects of the South Circumpolar region, which is the destination, of course, of a whole armada of international spacecraft in the coming decade. So let's first take a look at the characteristics of this international focus. Why are we doing this? Okay, well, the first thing is, of course, it's the scientific desire to get outside of the wonderful Apollo Luna Chang'e 3-5 region of the central northern near side, and also to really be able to try to address some fundamental questions we haven't necessarily been able to do before, which have a lot to do with fundamental aspects of the formation and evolution of the moon, particularly its early history. And most importantly, perhaps, is the role of the South Pole Aitken Basin, which you can see here. I should point out a third point here, which is if all the volatiles were located, maybe by True Polar Wonder or something, located here on the far side, we would not be going to those areas necessarily. We would not be establishing a base there because the reason we're going to the South Pole is fundamentally that we cannot survive lunar night. We need to be there with constant illumination. So keep that in mind, because whoever cracks the code of surviving lunar night owns the moon. And I think it's up for grabs, okay? So just keep that in mind. So let's talk about what I like to call the bedrock geology, which is a really kind of a misnomer for the moon. But we really want to know the provenance. Where did these rocks come from? We want to identify the major sequence of events and really assess what this means for the primary scientific questions that ones have to do with non-volatiles in this particular case. That's the focus here. And then what we need to do is think about how these influence human and robotic exploration strategy, because our acquisition of answers to these fundamental questions is only as good as our ability to plan traverses, to train astronauts, and to extract the correct data. So let's think about this, but first let's talk about what is so important. First of all, the global context. This is an unexplored region providing access to the far side and 2 major relatively unexplored lunar crustal terrains, the far side highland terrain and SPA that Brad Jolliffe described some years ago. It also gives us insights into the sequence of events because, in fact, we're looking at the post-crustal formation, 2,500 kilometer diameter South Pole Aitken Basin, and then, of course, all the features that have formed subsequent to that time, a whole slew of impact basins. If we could date these, particularly SPA and these other basins, then we have an opportunity to really deconvolve not only the signal from the moon and the origin and evolution of the moon, but the chronology for the solar system. So the South Pole location is indeed, the center is located at the South Pole, of course, within the SPA outer ring. And, this is equivalent to the Oriental Cordillera ring, but due to the multiple subsequent impacts, as you can see in the geological map here, and the overlapping ejecta here, this is really a hard nut to crack. It's more similar to the Apollo 16 Central Highlands complex impact polymech breccia dominated geology than to things we're used to before, like Apollo 15, 17, 11, 12, and 14, for example. So strategy, what we need to do is deconvolve this complex SCR history. This really presents a formidable challenge and requires an integrated strategy for site selection, traverse planning, sample assessment, et cetera, et cetera, et cetera. So let me try to outline a few of these points here. First of all, the South Pole Aitken Basin eject mantle sampling paradox. Hey, we're going to the rim of the basin. That's where all the good stuff is. Well, maybe not, okay, because SPA is likely to have been a oblique impact. Here's the South Pole, and most of the, particularly the deeper eject, is likely to be, in fact, in the distal part, not the proximal part. So we have to be very careful here and very selective and try to understand where that might be. If the South Pole Aitken Basin rim contains any mantle material, the most likely sampling locality is a steep sloped Mons Malapart here, and it'll probably occur as admixed, small breccia fragments admixed further by subsequent impacts, of which there are hundreds, okay? So we really need to be thinking ahead here about how we're going to carry this out. What about the geological stratigraphic framework? Well, there's good news and bad news. The topography is dominated by the SPA Basin outer ring, but that's here, okay, there it is. But it's complicated by multiple subsequent overlapping impact ejected deposits. As I pointed out, it's most like Apollo 16 in the Descartes Highlands. Detailed local geomorphology, like at Apollo 15 or Apollo 17, provides minimal, if any, clues to impact multiple polymeric breccia provenance, okay? So we have to figure that out in a separate way. So in the SCR, 20+ kilometer diameter craters, as you can see here, interleaved ejecta deposits, as we showed before in the ejecta overlap, at all scales dominate walking traverse and probably rover traverse sampling. So we need to be really careful and focus on how we're going to optimize this with the best possible mission plans. So a really critical part here is determining basin crater absolute chronology. We need a regional sample, but look at all these different craters here. We need a representative sample, and we also need to collect any exotics. If we're going to only be walking around for a short distance on the early missions, then in fact, we need to have a rake, okay, to get a very important representative sample, but also sample exotics thrown in from other places. Another point here is we'll be mapping secondary craters to get these other basins. If we're looking at a regional area, you know, of the order of radius of 1 kilometer or maybe 5 or 10 kilometers.
6 minutes.
Shock secondary craters and clusters from different basins, for example, from Oriental, are really going to be what we're going to have to use. Here's a map of all the craters greater than 1 kilometer post-Oriental, the youngest of the basins. This is, you know, horror show, okay? And not only that, they're not symmetrical secondary. So as you can see here from this work by Guillaume et al. So again, another part of it that we have to point out in detail, work on in detail. Pinpoint landing is necessary to ensure access to targets of crater basin ejecta, secondary and South Pole Aitken Basin mountains. We can't just land anywhere here. Look at all these different craters. They're all going to have overlapping ejecta. We need to understand that. Traverse design and mobility. If we take a look here, basically there are two major requirements that derive from the South Circumpolar region geology. Due to its complexity, okay, the time at individual sampling stations will be long, and the learning discovery intensive, the learning curve is going to be discovery intensive relative to Apollo. And this has a lot of meaning in terms of astronaut training and traverse design and mission planning design. We need mobility. Greater than Apollo 15, 17, tens of kilometers is required. And any kind of design reference mission CONOPS actually might feature long radially oriented traverses with multiple widely spaced long duration stations, fresh blocky craters such as those at North Ray on Apollo 16, and rover design should exceed the design performance of Apollo Lunicod, because in fact, Apollo Lunicod cannot safely access Mons Malapart over most of its surface, okay, as shown by Vasilevsky and others. So sampling procedures we need, okay, if we can't just sit there and triage polymeric breccias, okay, we need real-time handheld remote sensing capability to identify fingerprints such as mafic minerals, ultramafic, creep rich, etc. We need tools to ensure representative and diverse samples, such as a lunar rake. We need mobility to determine the regional technological variability, such as a lunar rover, and we need large sample return mass. Everybody get onto the Artemis program to increase the up mass and return mass, which is currently less than 50 kilograms per mission. Okay, here's where that lies in the overall scheme of Apollo. When you include sample return containers and things like that, that's a key issue that needs to be resolved. So finally, mission operations and science support, okay? there's a very steep on-site learning curve, okay? This is for the astronauts, okay? They will be learning a lot fast. This means that basically, remember the Apollo T-cube strategy, train them, trust them, and turn them loose. The situational awareness will always be with the astronaut on the ground. So the ground needs to develop a backroom psychology, which is kind of an advisor consultant psychology. And we need this because when we go to Mars, which is what we're practicing to do, crew autonomy is required. Okay, so let's go. There's tons of things to do, but we have a big challenge in terms of how we operate on the surface with these major constraints. And key among those is astronaut LRV mobility in order to get away from the walk-back constraints and really optimize this. Thank you very much.
Thank you, Jim, for an awesome talk. We have time for one really quick question, if there is any. Otherwise, I would like to move on to save us 10 seconds here.
And we'll have time.
Glad to contribute.
Thank you, Jim. And we'll have some time perhaps later on for questions. And again, please feel free to use the chat window for questions. That's always a good venue to raise and have a discussion. All right, I am pleased to introduce our next speaker, Brad Jolliffe and the law firm, who will be speaking on sample science for Artemis, collecting materials from the giant South Pole Lake Basin. Brad, you have 10 minutes starting now.
Thank you very much, Noah. And of course, who's the second author here? Yes, Noah Petro. Well, Jim, as usual, great context, and everything Jim said about sample mass, I will repeat here. I'm specifically interested in this talk about the possibility of sampling materials from South Pole Lake Basin. And so I'm going to take a slightly different approach to what Jim showed and back up a little bit and look at the compositional remote sensing that we have. Question is, how much South Pole Lake derived material will be there, and then how will we recognize it? So, science objectives associated with SPA Basin have been identified by the past 2 decadal surveys, and these objectives have to do with, number 1, determining the basin chronology, and that is not just the age of SPA Basin itself, but the ages of the large craters and basins within it. This will constrain the period of late heavy bombardment on the moon, as well as models for the early migration of giant planets and other interesting early solar system phenomena. Also, number 2, samples excavated by the SPA Basin may provide the first direct samples of the moon's mantle and new samples of its lower crust. Third, samples from SPA Basin will provide a test of models for giant impact basin formation applicable to all planetary bodies. Now, question is, at the Artemis landing site, and we're looking at the south circumpolar region here, will SPA-derived materials be needles in the haystack? I would argue that many samples would be needed to make statistical arguments to identify the materials needed to determine the chronology of the basin and find deep crustal and mantle-derived materials. So, picture's worth 1,000 words. Here is the Lunar Prospector Gamma Ray Spectrometer FEO map to a half-degree per pixel resolution, overlain on the LROC WAC mosaic. What you see is at the top part, that's the far side, southern far side, South Pole Lake Basin. In the middle is the south circumpolar region, southward of 84 degrees south latitude. And then at the bottom of the image is the southern near side feldspathic highlands. Well, a casual look at the south circumpolar region would suggest that it looks like pretty feldspathic material, low iron contents. But the idea is that SPA Basin, as Jim said, has its southern rim pretty much right at the South Pole. And some of the massifs there, in fact, are basin rim massifs. And so what's the possibility that some of that material is actually in there? Let's take a closer look at the compositions. So a hypothesis and a test. Materials ejected from the South Pole Lake Basin along its southern rim were deposited within the south circumpolar region. Of course, that was over 4 billion years ago. So subsequent impact history and ballistic mixing of deposits have diluted the southern SPA rim deposits. but some portion of the SPA rim deposit substrate is still present in the south circumpolar region. And these materials ought to be found among comprehensive samples collected at the Artemis 3 landing site. So my test here is to use Lunar Prospector gamma ray spectrometer compositional data to determine mixing proportions of these two main classes of material, SPA basin materials and feldspathic highlands. And here we'll use the southern near side feldspathic highlands for the test. Now, a key concept is that of ballistic sedimentation. I show on the right-hand side a model from Larry Haskin from almost 20 years ago, where he made the argument that ballistic sedimentation, you can begin with a substrate shown on the left-hand side here that's entirely SPA ejected deposited material, and then have many subsequent impacts that serve simply to mix materials in and dilute that substrate, but they don't eliminate it. And ballistic mixing makes it a deposit that's well mixed. This is not layering, this is percentage of materials. So there should still be SPA ejected materials there. Well, let's take a look at the iron. Here, I'm just going to simplify things by taking a traverse from A, from the south central portion of SPA, to B, southern near side feldspathic highlands. You can see the SPA materials are high in iron. There's the average. Through the south circumpolar region, the FeO content decreases. There's the average. And then on the near side, it's still above the feldspathic highlands, but still decreasing. And then we get into the feldspathic highlands, which is lower. Now, if you do a simple mass balance model, what you find is that within the south circumpolar region, on average, taking the average compositions, there ought to be about 40% SPA material and 60% feldspathic highlands. Of course, SPA materials higher on the far side of the south circumpolar region, 55%, and lower on the near side, 27%. Okay, kind of interesting. Well, let's take all of the major elements and thorium from the Lunar Prospector gamma ray data, and we'll use 5-degree data here now because we've got other elements that come into play. And here you see thorium versus iron plus magnesium, same kind of deal. South Polacan Basin, higher thorium, high iron plus magnesium. Feldspathic highlands, low iron, low thorium, and south circumpolar region in between. Now, the way the data points, the averages are arranged here, you get the idea, plus the way the labels are arranged, that the SPA percentage is going to be about 20% on average and 80% feldspathic highlands. For the circumpolar region, far side, a little bit more, near side, a little bit less. Of course, with 5-degree per pixel data, that's not a whole lot of resolution. And so the resolution is not as good as it is with certainly the 1/2-degree iron data, but you get the same sense. So sort of conclusions, will there be SPA material and deposits at the south circumpolar region, poleward of 84 degrees south latitude? Yes. And a non-trivial amount, on the order of 20% or more on average. Of course, that'll be more on the far side part of the south circumpolar region, less on the near side part. Will this material be easy to find? Not necessarily. It'll require many samples, careful analysis, compositional analysis, age determinations. And these materials will likely be as or in complex breccias, like this beautiful Apollo 14, 14321. That's Big Bertha, the largest of the Apollo 14 samples, a beautiful breccia. And the SPA materials may indeed be things like clasts within a breccia like this. So stay tuned for Carly Peters' talk after mine. Sampling for Artemis 3 must include comprehensive samples, systematic kilogram plus regolith samples, and sieved or rake samples to concentrate and collect hundreds of small rock fragments and a few big ones. Artemis 3 astronauts, please bring us back some breccias like 14321. And finally, I'll just end with SPA science will be enhanced enormously by a separate robotic sample collection from the interior of South Polacan Basin. Thank you.
Thanks very much for that, Brad. We have 2 minutes now, and we have a question in the chat window from Carolyn Vanderboger. And so I will, unless you have it up, I will recite it to you. Brad.
I'm looking at it.
Okay.
Go ahead and read it, Noah.
Do you think you can get an SPAH from feldspathic basin impact melts derived from the crust that have been excavated, for example, taking the oldest radiometric age? Or would they be hard to separate from other feldspathic materials? Brad, the ball is in your court.
Well, yeah, okay. I'm not sure I quite follow, Carolyn. What we're looking for are mafic impact melts and mafic materials. And you know what I think we'll find are a lot of the mafic materials in the South Circumpolar region that give us that SPA signature will be materials that have been excavated and possibly ages reset by other big craters. I mean, think about something like Antoniadi, but Antoniadi struck SPA basin substrate, and so the materials, and if there are clasts that retain zirconium phases or other phosphates, other ways of dating the materials, we'll be able to get those ages. And I think it's going to take a lot of analyses before we see that sort of bookend of South Pole Aitken Basin age. I'm not sure that answers your question because you're asking about feldspathic materials, and I'll be more interested in the mafic materials.
All right, we need to move on. The next talk will be given by Carly Peters, and she presents work by her and colleagues on the probability of Artemis collecting deep-seated material excavated from SPA to South Pole is tiny unless. So I hope Carly enlightens us, unless what?
I'm trying to get my screen up. Let's see.
Okay.
Desktop, okay.
We can see your desktop.
Oh, okay, can you see my slides?
Looking good.
Okay, very good. Well, it's tiny unless, and I'll jump right to my conclusions, a human robotic partnership is established that includes modern instruments, training and site planning, and a robust infrastructure. So I'm sort of the third bump on the log, but I'm going to re-emphasize many of the things that have already been said. Okay, well, Apollo and Luna sampled sites are all on the near side, and there's right now none on the far side. However, the South Pole is about a hemisphere away from sampled terrain, but it will be close to sampling, or it will be the closest sampled site yet to the South Pole Aitken Basin, and might, perhaps can. I'm not as optimistic perhaps as Brad, but if we do it right, I think we can get it. Okay. What should we expect? Well, by now you should have heard both from Jim and from Brad what the basic character of the terrain is. Several years ago, the master, Malash et al. Did a model of the impact itself and distribution of the ejecta. As was mentioned, we believe the impact forming event was oblique, and this has very strong implications of where the deposits go. Okay, where the deposits go in on the moon. Dan Morardi just recently took the Malash model and put that into geologic context as well as composition. And what you see on the right is the distribution of the predictions of where the ejecta from South Pole Aitken would be deposited after the event. Now, most of us are familiar with the South Pole. The most common view of it is shown on the left with the beautiful LRO mosaics that show how deeply shadowed the area is. What's shown on the right is what the LOLA, the LRO LOLA laser altimeter provides. These are both reflected data. However, with the laser altimeter, you can look at the surface without any shadows. You're looking at a shadowless moon, and it looks familiar to you. However, now you're eliminating the shadows in the normal solar illumination, and you can see that yes, the South Pole is part of this feldspathic terrain that Brad was talking about. Let's look at it in a little bit different perspective. Again, comparing with some of the information we've already discussed. The South Pole is in this vast high albedo terrain, which we know is largely the feldspathic breccias compared to the darker iron-bearing basalt and the interior of South Pole Aiken, very similar to what we have sampled at Apollo 16. And again, showing the low iron distribution as seen in the gamma ray spectrometer data. So this is a completely consistent story, but it's telling us that it's primarily feldspathic breccias and not the, and right now we don't see any of the abundant mafic minerals at all. Well, now samples from the South Pole Aiken, excuse me, from the South Pole are extremely valuable. They're unsampled breccias with very low creep. We only have Apollo 16 and Luna 20 that provide us information about this kind of terrain. These are extremely baseline important samples to obtain to understand the feldspathic character of the moon. Of course, the reason we're going to the South Pole is we know there are volatiles there, and we're very interested and eager to sample them. How we sample them will be a challenge, but we're guaranteed to, or almost certainly guaranteed to get volatile samples. However, now, and the third is that the samples just might, perhaps can contain some of these exotic components, even though they don't show up in the albedo data or in the detailed overview that we see. Finding these unusual samples is going to be hard. Now, why is it hard? Even for a well-trained geologist. First of all, and I think you're all familiar with this, that there's very persistent low illumination, deep shadows. Think of going out at midnight on a moonless night, having a spotlight behind you and trying to find your way around unfamiliar terrain. Oh, how hard is that? Secondly, and Brad and I picked the same allegory, looking for these are going to be a needle in a haystack. They're very small compared to the bulk character of the environment. Well, that's where efficient human robotic partnership are needed. And there are three elements that I want to walk you through to talk about that. First of all, what is human robotic partnerships? Human astronauts are uniquely adept at assessing environments and adjusting actions to be the most beneficial to achieve goals. That's why we send humans for exploration. However, at the poles, human perceptions are going to be severely limited. In contrast, modern instruments are designed to provide attuned and specialized eyes to provide the information that we really want to see that we can't see with our own eyes. And it's humans and robotics working together that are not only efficient, but achieve results superior to either one of them working alone. Okay, well, there's three elements that I'm promoting. First is modern instruments. There are several sessions in the forum that address examples of some of the modern instruments. What's needed is not only the instruments themselves, but we need the infrastructure that will allow the data themselves to be returned and worked with the planning for what the astronauts are working on the surface. That said, the training and site planning needs to incorporate this in their training. Astronauts and science teams who are familiar with these instruments need to be working together so that they're a well-tuned partnership. Okay, the third and most important, because it hasn't been mentioned and there are no US assets of this currently in place. I was glad to hear the Europeans mentioning this as a goal in their presentation earlier this morning. But what's needed, which is essential if we're going to have this partnership, is a direct communication that includes high bandwidth. You don't want to cripple these instruments by having a low data throughput. You need to have a continuous infrastructure link so that as the astronauts are sleeping, the parties back in the back room can be madly assessing where things are and where the most valuable use of the astronauts' time might be. Second or last, you need two-way real-time communication. The back room needs to be part of this whole package, obviously through appropriate channels, but that's very essential because of the nature of the South Pole and the situation that it's in. So let me come back to my conclusions. If it's not obvious now, after all three of us, the probability of Artemis collecting deep-seated material excavated from South Pole is really small unless a human-robotic partnership is established that includes modern instruments, training and site planning, and a very robust infrastructure. Thank you.
Thanks, Carly. We have about a minute of time here. And I promise to my co-convener we won't eat into your time, but does anyone have a question for Carly? Question in the chat window.
Go ahead, Noah.
Where can we sample representative SPA material within SPA?
Oh, well, okay, Brad can answer this probably better than I can. Clearly, it's going to be a complex challenge, but certainly one that is doable, because once you're in the middle of the basin, you can unravel this impact history and identify some of the prime areas. You can get the diversity that includes ejecta and subsequent events. So that's a whole nother planning activity. Would love to do it.
Thank you, Amelia. Just walking in here. We're going to transition now to my co-convener, but Carly, there are some other questions that are being followed up on in the chat window. So I would encourage you to hop in the chat at your convenience and join the conversation. All right, now I'm thrilled to introduce my co-convener, Hannes Bernhardt, who will be presenting on the identification of new science targets based on mapping at the 1 to 10,000 scale of the Artemis 3 areas of interest 001 and 004 on the Shackleton-Dagerlash Ridge. And I will put up the timer in a moment here, and I'll let you get started.
Thanks, Noah. So, so this is work based primarily on high-scale mapping that I've conducted in recent months based on NAC imagery. I'm going to start off with a few regional aspects that need to be considered if we look at the area immediately surrounding the Shackleton crater, specifically areas of interest 1 and 4, according to the Artemis report. So what you see here is something that Carly already showed us in her talk, is the low albedo map of the South Pole area. What the arrows point to is a ray that seems to be emanating from Tycho, and it's one of the most prominent longest rays there are. Actually, it extends almost to Lyman crater on the far side. And you can also see it on wet color imagery, which you see on the right-hand side. It's a stretched version of that. And the arrows, as well as the red little mark outlining the mapping area, actually you see how small it is because it's a high-scale map. They point to exactly the same locations. So it lines up very well. And as we will see on the next slides, it comes pretty close to the actual area we're looking at. So this is now zoomed in onto the South Pole. You see the PSR of Shackleton in the middle marked with an S. And you can see different outlines of ejecta blankets as they were mapped by various authors. In this case, Spudis, Krasnilnikov, Nivanov, and Halim. None of those correspond to any geomorphic signature that I was able to see, except in very small portions. So overall, these are the Shackleton ejecta does not have a sufficient geomorphic signature to really map its outlines with any confidence. However, low albedo data as well as wet color data can show you signatures that seem to be co-aligned with Shackleton and sort of with its ejecta outlines if they have been proposed. So you see the generally higher albedo area around the South Pole and the low albedo pane on the left. What you can see also is a dashed line tracing the Tycho ray, which is about 10 to 15 kilometers wide. If you try to measure its low albedo signature in less disturbed areas, it intermixes with the sort of brighter area around the pole, and that might either be that brighter area might either be Shackleton ejecta signature or added to the Tycho ray, or it might be the less mature soil that we would expect, less mature regolith would be expected at the South Pole due to decreased space weathering in the area, as we would expect for both pole areas. So we can differentiate between either of those effects in the white color data. The higher apparent albedo here might be due to the geography, the geometry and of the geography, specifically because all the slopes are equator facing away from Shackleton, the outer walls of Shackleton. So we expect higher apparent albedo in the imagery here. So we can't really differentiate between either of those effects. Suffice it to say is that the entire mapping area, as outlined in black here, probably is affected by Shackleton ejecta, the entire area. So this is the geomorphic map as it stands right now. There is, so all of the units are purely geomorphic in nature. As Jim had rightfully pointed out in the very beginning, geologic map of the moon is a problematic term in itself. What we're mapping here basically is a regolith texture, which is primarily determined by slope processes. That is, for example, in the most extreme case, the brown unit, which we dubbed, at one point we dubbed the texture ground tree bark terrain or elephant high terrain. There are various names for it. And it shows slumping by regolith creep down slope. All the little furrows are usually perpendicular to the local slope gradient. There are several other features of note that I want to point out here, is that the blue unit, crater fill unit, is a very smooth unit that sits only in the centers of some craters, and knobs that are very difficult to see here, but because they're so small, but I'm going to show you a zoomed in version in the next few slides. This map is going to be available on QuickMap, our QuickMap, very soon. It's in the beta phase and it's going to be released in the next few weeks. So you can peruse at your own discretion. There's also a potential, I repeat myself, a potential lobate scarp that is located in the south of the, or what appears to be the south, the lower portion of the map as you see it right now. This is still under investigation. It's not a very distinct feature, but yeah, those are just some of the highlights I want to point out. There are different crater classes that we differentiate between based on their apparent freshness and also the occurrence of blocks around them. Now, I'm going to zoom into this area and I'm going to talk a bit more about blocks and potential traverse planning based on the mapping. Now, what you see here is a traverse plotted according to its topography as well as the slope, and the little boxes in the map are block detections. Most of them are based on Gary et al., which is the following talk, which I highly recommend. I verified most of their findings. Some of the potential findings I could not verify and did not include. And I always used at least 3 NAC images that I need to see a block in order to call it verified, at different lighting conditions, of course. So what I did basically is I start to traverse in a very level area around the red patches you see circled here. Those red patches are the high illumination areas for the considered timeframes, more than 70% sun illumination. And there are some blocks around there right away that we can drive up to or visit with whatever means. by foot or wheel. And the traverse continues on the Shackleton-de-Gerlache connecting ridge, visiting as many blocks as possible without going beyond a certain slope threshold. And the first stretch of the traverse will not go beyond 10 degrees. Then there's an extended traverse, which will accept slopes up to 15 degrees. And then there's what I call an increased risk extension, which will accept slopes up to 16.5 degrees, which is probably beyond safety parameters, which is why it's called increased risk extension. The extended traverse will get you all the way to the rim of Shackleton, and you see the amount of blocks that are going to, or rock exposures that are going to be visited. To highlight a few, here's one of those aforementioned knobs. Goranska et al. Were the first to point them out, really. We are not sure about the nature of those. They might be ejector blocks, weather down ejector blocks from the Shackleton event. That's going to be visited with that theoretical traverse. There's a very fresh crater with beautifully exposed blocks around it, and also ejecta visible on white color. It would be visible, visited in the increased extension. And last but not least, this is pointing to the wrong direction, wrong location. So this should point to the blue area, the blue CF area inside the crater. On the top, you see it's very smooth crater floor, and there might be distinct material, possibly impact melt, that would also be visited at the very end of the traverse. Thanks for your attention.
Thank you so much. We have time for one quick question. A question in the chat window. How are the NAC images co-registration issue resolved for defining the absolute location of blocks? There's a lot to unravel in that question, so you might start here and then follow up in the chat window.
Yeah, of course. I manually, so the NAC images were manually corrected in terms of their georeferencing based on crater locations. Now this is an imperfect process, of course. Shadowing, very long shadows of the blocks can easily give them away. And if you have two different images showing in different lighting conditions, the shadows point to the exact location of the actual block that's sitting on the surface casting the block. So that's a good way to, within pixel range, determine the block location.
All right, and you can follow up in the chat window, but I'll turn the ball back over to you for the introduction of our next speaker.
I have to stop my screen share first. There you go. So I think we should move on for now. And the next speaker will be Brent Gary, as I mentioned before, and he's gonna talk about what I hinted at already, the distribution and geologic context of boulders and outcrops along the connecting ridge at the Lunar South Pole, connecting ridge at the Lunar South Pole exploration site. Take it away, Brent.
Okay. I'm gonna quit and restart because Zoom is horrible. So hold on.
Hang on, hold.
While we wait for Brent to get good comm, why don't we take a moment to maybe invite our previous speakers back up to the forefront, and I guess maybe one question, Hannes, and you've identified some boulders. We'll hear in a moment from Brent about the boulder identification work that he's been doing, and this kind of maybe echoes the question that I raised with Carly. We have these boulders, wonderful. We can sample them, but what specific tools would we want to bring with us to the field? And maybe Brent is back, and so we can table that question. So, all right, Brent, never mind.
Oh, sorry. Okay.
Quite all right.
Had to enable ability to share my screen. Okay, thank you. Sorry for the delay. So I'm going to follow up based on the last talk and talk about more of a specific map of boulders and outcrops along this connecting ridge region in the Lunar South Pole. So Apollo returned several beautiful images, as we see to the right, where they visited multiple boulders at each landing site, some kind of small boulders, and some boulders that are large, towering, way above them. Some were along the crest of crater rims, and some had rolled down the hills like at Station 6 from Apollo 17. So lots of reasons to kind of target and think about visiting boulders for Artemis. Once we start figuring out where we want to go, we want to look at what geologic features are located, where they're located, and how that can help us inform our science mission and planning. Now, depending on your point of view, boulders might be good for science, as was on Apollo. And if we even better, if we can get to outcrops that were observed, like at Rima Hadley, but a little too difficult to sample there. So we want to be able to target those for our traverse planning, since we'll still have fairly limited time during these missions. But from a different perspective, from a landing perspective, boulders can be viewed as a hazard. We're coming up on the anniversary of the landing for Apollo 11, and you may recall Armstrong saying, hey, there's a pretty rocky area there as he dodged a boulder field associated with West Crater. So I encourage you to jump into Ben Feist's Apollo in Real Time for Apollo 11 shortly after this session to catch that landing, and you can see that boulder field right there in the window of the LEM. So each landers will have a ground clearance limitation, so we want to know not only where these boulders are, but how big they are. And so a spatial map of these boulders and blocky craters will help inform the placement of various landing ellipses in an exploration zone. So for this case study, we went to the Connecting Ridge, or we're studying the Connecting Ridge, which is that little area between Shackleton and Degerlache, known for its high illumination along the crest ridge as determined by Mazarico et al., as well as its access to permanently shadowed regions. So zooming in, our study area is about a 16 by 16 kilometer section. There's a top-down hillshade view on the right and a perspective view that looks along the crest of the ridge towards Shackleton, the rim of Shackleton crater there. There's a little letter A that marks the same crater in each image. You kind of get a view of where you're looking at. So we really wanted to document how many boulders and other features are in this area, and build on previous studies that have looked at boulders at the Apollo sites as well as along the rim of Shackleton crater. So what are we looking for? These, whereas Hannes made more of a geomorphic map and kind of beautiful polygons, we're looking at making more of a point feature map. So we want to look at boulders, which we can identify here on the bottom left with kind of these bright albedo faces, these really long shadows that come from the extreme lighting at the lunar South Pole. And you notice it has an opposite shadow pattern from the crater that's nearby. We also want to look at outcrops or exposures, like kind of these mounds that have these illuminated faces. Sometimes they might have even more of a layer-like appearance without a shadowed tail. So we want to identify where there might be exposures. And we also want to identify the location of blocky craters like we see here on the right. So kind of things to avoid with larger extent of a boulder field, things that we want to avoid during landing. So these are just a few examples of what we've been mapping. To do this, we started with the NAC average mosaic over here, which is a work of art in itself, but there are a few artifacts and some of the areas are washed out, so it's difficult to see all the boulders. So we processed a series of mosaics. Essentially, we filtered them out in LROC QuickBack by their solar azimuth to give different lighting conditions, lighting as well as to slightly different resolutions. So between 0.5 meter per pixel to 1.6 meter per pixel. So this shows the features that the mosaics that we looked at in ArcPro to map the boulders and outcrops. So here's the map off to the right. As it currently stands, we've mapped close to 1,500 different features. Some of the main things we look at, the green triangles and yellow triangles, are boulders that we think are pretty definite, and the yellow triangles are kind of possible boulders or something there. But might not be sure if it's just kind of something buried or if it's actually a rock sitting on top of the surface. We've mapped outcrops, which are the orange squares, which are located all throughout. And then the pink circles mark the blocky craters. This is viewed about 1 to 50,000 on the right. There's a little yellow triangle right up here that shows this inset. So when it's zoomed out, all these features look like they're right on top of each other. But when you kind of start zooming in to looking at this NAC image, you can see how they're spaced out. And even this closer little inset, which is marked by the yellow arrow, you can see kind of maybe something might be an outcrop or boulder next to about 3 different boulders right there. So just to give you an idea of what these things look like when you start zooming in and how spaced apart they can be. Just an example of some of the blocky craters. This is one of the more denser areas of the map. You see 2 craters right next to each other. I'm just going to flip between them so you can see where the boulders and some of the outcrops are. We've also done some polygon features where we've marked the crater rims as well as the extent of these boulder fields that are associated with these craters. Once we have this map, you can be like, hey, what can we do with all this information? So we can do the slope map, say, hey, where are boulders that are on slopes less than 10 degrees or less than equal to 10 degrees, which are, might be something easier to walk to or get to for a crew or even a rover. You also might want to say, hey, where are the boulders in the higher illumination areas? So where are boulders that are illuminated greater than 70%? So we can kind of query the data sets and get a little subset map of just those features that are boulders less than 10 degrees and boulders in the higher illumination area along the crest of the rim there. We can also say, hey, where features are close to the permanently shadowed regions. So we can create a little buffer, maybe a 100-meter buffer around the permanently shadowed regions and figure out which boulders we might be able to visit as we go into PSR. Now, one of the key things about these boulders, it's easy to measure their width, it's easy to identify where they are, but trying to figure out how high they are, how tall they are, can be difficult, especially with the extreme lighting. So the terrain has a very big influence on the shadow measurement. So if you just take a measurement of the shadow without factoring in the change in the terrain, you can get very different results. So just a simple 3D graphic model off to the right, you see the same boulder against a hill or on a flat area or at the crater rim. And on the right, you're looking top down as if it's a feature or a spacecraft. And you see just how the shadow changes if it's going up a hill on the flat area or down into the crater. So this is important because as we take measurements, if we just measure the shadows on this cluster of boulders here, it would give us a range of, it would tell us that it's about 20 centimeters high. But by factoring in the elevation, we're getting closer to 2 to 3 meters, 1 to 3, 70 centimeters high for these different clusters of boulders. So these are measurements from 2 different images of the same cluster. And they kind of give us some reasonable idea of how tall these features are. So a little something we need to do for everything else. So a good thing to think about is what do these features look like once we get there? So you can train yourself by looking at the Apollo surface images. You can see house rock in the background. And what does that even look like in a NAC image? So you can see that off to the right here. So I encourage you to look between the two to compare what these features look like from orbit and what they might look like from the surface. So these maps will help us figure out where we're going and what we'll find when we get there. They help us anticipate the local geology for landing. They help us provide spatial information for planning traverses, as well as even potential real-time multiple mission scenarios for planning multiple mission scenarios and decision-making during a mission. So with that, I'll leave it there for any questions.
Thank you, Brent, so much. This is awesome work. We have one question by Jim Skinner in the chat. Nice work. Might it be possible to use both points and lines and polygons for outcrops? Points might not capture the full extent of the accessible area.
Yes, so some of the things I didn't show just due to map clutter is mapping out the length of some of those outcrops with a line. So I do have a mixture of line features that can be used to map kind of some of the more elongate or linear looking outcrops and features, and polygons to map out some of the broader extent of an outcrop. Yes.
Awesome, thank you. I think we should move on.
All right, it's my pleasure to introduce our next speaker, Kasun Mahanti, who will be speaking on secondary illumination in large permanently shadowed regions at the lunar PSRs. So, Kasun, why don't you take it away?
Hi, can you hear me all right?
Yeah, Prashun, you have to swap displays. We are seeing a notes pane.
Okay, hold on.
In the top left, click swap displays. Now on the previous view, you can play from start again, and then swap displays. That should do the trick.
Okay.
Hopefully.
Okay.
There you go. Thank you.
So, so this presentation is about the ongoing work that we are doing with respect to simulating the secondary illumination at the permanently shadowed regions. And this particular presentation is only focusing on 3 large craters out there. So we'll start off. Over the last more than 10 years, the LRO has actually captured a brilliant set of images of the polar regions, which actually has enabled us to look into the illumination conditions at these permanently shadowed regions. Well, the permanently shadowed regions don't have illumination, right? Well, the LRO cameras were able to actually image inside the PSRs using the reflected light from the crater sites, the walls, and the areas on the top of the walls towards the rim of the crater. And what this actually tells us is that there is some illumination which is present on the PSRs. And if you have a camera which is sensitive enough, then it can actually capture those images. So, but how do you make the connection, and how do you actually get towards about the sensitivity of that camera itself? In order to know that, we need to kind of try and understand what is the degree to which the radiant energy is present at the PSRs. And that's what we are doing here by trying to simulate the secondary illumination at these PSRs. So we know that, actually, I think I already spoke about this slide. So this is one example where I'm actually showing, so the left side of the screen actually shows the primary illumination that's been collected over 6 months, okay? This particular map was made like 10 years back from now. And the second one on the right-hand side is actually an image where we have increased the NAC exposure time by about between 20 to 80 times, which actually causes a pixel elongation, but you can now see the floor of the crater and you can see the geology, which means that if you increase your exposure time, that means you're adding up signal. And if you can do that, so either you have a very sensitive detector or you need to add up signal. So using NAC, we could do this, but NAC was not meant for this kind of purpose, right? So then what this also tells us that across the crater, the primary illumination keeps on changing. Now this is another stack which has been collected. So this is, the entire thing is simulation here. What it is trying to do is that it is trying to simulate the primary illumination, that is the radiant energy coming directly from the sun on the walls and on the floor of the local region. And you can see that the inside of the Shackleton crater is absolutely dark, right? What we are trying to do then is that if you look at if you look at the rim gets illuminated. What you are trying to do is to find out is to have a method to actually use the illumination from the rim being scattered on the floor and then try to find out how much of that energy is still there. So this is another example. I snuck in a North Pole example here in the South Pole presentation, but this actually shows us the best image, one of where we can actually use just the secondary illumination, which is actually present, to take a really cool picture of the geology out there, which means that with a much sensitive instrument and or with a longer exposure, we should be able to do that. And another example on the right-hand side is a South Pole PSR mosaic that we have created out of these long exposure images. So what are we doing here? Basically, what we are trying to do is that we are trying to model the secondary illumination, which is the reflected light from a facet. I'm not going to go into the depths of this because I like to show some full simulations, but we can get back to this if you want. So basically, the idea is that we find out the degree of interaction between a facet on the wall of the crater, which emits the primary, to the floor. And that computation is done for every point on the floor, and by which we actually end up getting this model. So basically, once we do this, we have a primary illumination, we have a model for the interaction parameter, and we get a product to which tie down to every observer on the floor of the crater. That's what we do. I'm not going to get into this. This kind of describes the degree of computation overload that happens when we start to do this. this is an example of one of our results. This is the floor of Cabeus, and the top part shows a mosaic obtained by NAC. The bottom part shows something obtained by the model. One example of the simulation is here. This is for the secondary simulation, illumination simulation for Shackleton. Now, if you can follow, just follow the primary illumination tip of where it is illuminated, and then if you follow the secondary illumination, you will see that they're exactly opposite, which means that the light is getting reflected on the other side compared to where the light is coming in on the crater. And that gives us a very useful information as to planning a mission to take images inside the PSR, right? Another example I'll get to. So this is for Cabeus. Now, all these craters are large. There is a reason we selected only the large craters. The large craters actually take up most of the area of the PSR region. However, because they are large, the light which ultimately comes down to the floor is also really small. So they are large. They are larger areas, but they are smaller in signal. Okay, so this is another example for Cabeus. This actually has a really small amount of signal. We'll let that play, and then we'll go to the third one. Okay, in some of the simulations, you will be seeing this green color, which basically means there is no illumination. That represents the 0 point. So you're not going to get secondary illumination at every point. And understand this, that this simulation tries to span the entire subsolar longitude and latitude, which basically is the illumination condition. So it's the entire domain of illumination conditions. And this is not what is going to happen in a mission. In a mission, you'll only sample a couple of these conditions. So basically, the ConOps of the mission has to be tuned to exactly being there at the right time to take the right picture. Okay, this is another. Okay, so this is for Amundsen. So this is exactly what I was talking about. This represents a point. There is no illumination coming from the primary side. As a result, there is no illumination for the secondary. And if you notice the plot, the last plot on the right-hand side, you'd see that only particular zones are actually bright compared to the others. Those would be the zones which will be, the ConOps of a mission should actually target, because that's where you have the best possible illumination. Okay, so these are the final results from the simulation, and you can see on the top set you have the secondary illumination maxima, and on the down set you actually have the actual images, the mosaics from NAC, and you can actually compare very clearly with them. They will have comparative contrasts between each point to point. And what was actually done in order to get the first top set is that you simulate all those different conditions, and then across the entire stack at each pixel, we just get the maximum value, which also shows us, in fact, that the NAC images were actually captured at pretty much the best possible time. Right. Okay, so what does this ultimately lead us to? It tells us that the radiance measurements from the NAC long exposure images and topography simulations, they are tied to another crater, Shoemaker, but then it is actually compared here with 3 large PSRs. However, when we do that, there is a statistical convergence of the analysis from the simulated data to the actual NAC data. What we find is the upper limit of the radiance was 0.2 watts per meter squared per radiance per microns, which actually tells us that the radiation, the amount of illumination present is really small here. And the highest radiances were actually obtained at the South Pole summer and subsolar longitudes. And I'll go to, so just so that small PSRs don't feel bad, we are doing the simulation for the small PSRs, and this is one example of small PSR. The difference that you would immediately notice is that for the small PSRs, the degree of radiance is really high, which makes sense because the smaller PSRs, the walls are closer towards the floor, and you have way more secondary illumination there. Okay, and I think I have another example. I took this one very specifically because I don't know if someone recognizes this shape, but that's the end of my presentation. And that also shows us another situation where the PSR actually does not happen only on a crater floor, but on the wall, and it's on a high slope. With that, I'll end my presentation and take any questions.
I think we're going to have to move on to our next presenter, but we will have time for conversation following the session. And so please stand by. And of course, folks are free to raise questions in the chat window.
Our next talk will be given by Caitlin Ahrens, presenting work by herself and Noah Petterall. And it's titled Shedding Light on the Darkness, Diversity of Permanently Shadowed Regions at the Lunar South Pole. Take it away, Caitlin.
Thank you so much. All right, so if I were to describe to you how in the world do we actually classify PSRs, in my analogy, I kind of consider it as like if I were to give you a rock. You know, would you describe it as what's the grain size of it? Maybe how heavy is it? You know, how does it smell? How does it taste? We all have classifications for something. We're all geologists, or most of us are geologists here, and we love to classify something. And so when it comes to figuring out what in the world these permanently shadowed regions are, we've kind of gotten into this overall sense of, oh, it's just water ice, it's just volatile ice. So in this case, not necessarily the case here though. So really brief overview though, these are just really, really, really cold spots. They will be somewhat have variations in seasonal temperatures, typically below 110 Kelvin, but some areas can go up to at least 250 Kelvin and then all the way down to 30 Kelvin. So huge swath of temperatures, but I'll get to as to why that's actually very interesting here in a bit. As our previous presenter just made ourselves aware of, is illumination is also something to be aware of with these PSRs. In that case, the topography would also play a role as to how are these PSRs even accumulated and crystallized. So it's not just temperature variations, it's also just all this accumulation of these different kinds of volatiles. So these are just very open questions. We're not going to be able to answer these right off the bat. These are very, very simple questions, but with very complex means of answering them. So how are these volatiles formed? What kind of volatiles are we dealing with? And then looking down at the grain size scale of these PSRs, the crystalline structures, the sublimation versus the accretion. So all comes down to location, location, location. Now, granted, this entire session is the south polar region of the moon. Okay, great. But what I mean by location, location, location is where are the volatiles in relation to their crater? Are they completely enveloped into the crater? Are they more maybe on the wall? Are they on the wall and the floor? So where are they located within the crater? And that's what I'm meaning here. So taking a look at certainly with WAC and NAC imaging, LOLA, and then also Diviner is also a huge help here as well with the glorious temperatures as well. So we get this beautiful Diviner data with the bolometric temperatures that you see at the top here. So you might just see like, okay, there's a lot of blue and purple here. That's great. There's a lot of cold spots. But now then it comes time to, it's not just water ice anymore. So these are about the maximum temperatures that some of these volatiles would be frozen at. And so it's, again, not just water ice. It's so fascinating. You can have sulfur types of volatiles, CO2, ammonia, and then getting into hydrogen sulfide and sulfur dioxides. Julie Mitchell is actually doing some amazing work with these types of volatiles as well, and her and I have been chatting a lot on these types of different kinds of fun ices. So in its complete barest sense, types A, B, and C, and D, I know, we're so original, but if we were to just go completely by location, it does not tell us the full story at all. So in that case, how about the size? What can we do about the size? how is the size of the PSR related to the size of its crater? Well, okay, there could be some minor relationships here though, with some dots potentially overlapping here. So let's dig deeper then. Yep, so there's our crater ratio. Going deeper then, how about the slope? At what angle are some of these PSRs even located with means of their crater? So thank you, Miriam Lemelin, if you are listening, and thank you for your slope angles in your latest 2021 paper. That has actually been a huge help. So in that case, looking at the slopes and how those slopes may have affected some of the accumulation effects of these PSRs. Yeah, okay, now we could start to see some of those distinctions, but there's more. Yep, so there's our slope differences. Now we want to see, how about temperature? How do all of these different types have to do with different kinds of temperature though? So looking at the max summer temperature, a good portion of these are well into the water ice, maybe a little bit of the methanol, not so much at the more exotic ices until you get into your winter temperatures. Now you start to get into all the really pretty exotic ices there. The little ellipse that I have here is the type C and D. A bulk of them happen to be just around the methanol water ice regions, not necessarily the exotic ice. So that's something to look into very shortly. So then if we were to just look at the temperature difference, your summer and winter, or maybe your summer maximum and summer minimum, how much of a temperature range do you get? Because the larger the temperature range, the more your crystallinity is going to be very unstable. So with all of these combined, now we can have a better sense of what the different types are with these PSRs. So a very basic map that Noah and I are working on right now. Really pretty color coding there and whatnot. But then real quick, how about the height at which these PSRs are found within their crater versus the length? How far into the crater are some of these found? So this is something called the HL ratio. That I myself have done with volatiles on series before. So if we use the kind of the same technique here, this ratio can certainly be not so much of the friction of the ice, but so much as the crystallization of the ice. In which case there is no relationship here, and actually that tells us a lot. Because there's, it just looks like a complete mess right now. What this means is that the grain boundary at the crater wall or the floor is actually affecting how it's being accumulated. In which case the PSR itself is actually not homogeneous. It's not just a water cube, a water ice cube or anything. It's very crystallized. Yes, so that's pretty much what I just said there. So why have a classification? Good for us, it's type A, B, and C, and D. But in reality, knowing the different kinds of crystallization types and knowing the different kinds of thermal variations that we can have can really help us out with further exploration, especially with Trailblazer and Viper, eventually to Artemis, figure out like, okay, where are the pure water ice water spots, and then where's the carbon dioxide spots, and then also where's the ices that you want to be really careful of, especially the hydrogen sulfide type ices. So there's always sorts of fun ice exploration, but then there's some safety and hazards. But also I answer at the very bottom, why not? Just why not? So I'll leave it to this slide again as to the open questions regarding PSRs, whether this includes the classification or not. But we should probably better understand just the crystallization and just the grain physics of these PSRs further. And that's my talk, so thank you so much.
Thank you so much, Caitlin. We have a question in the chat window from incomparable Jennifer Hellman. To what resolution are you assessing minimum maximum temperatures across a PSR? Within any PSR, there can be variability in temperature as a function of location within a PSR. What is the level of detail that you can assess in that range?
Very good question. So I'm mainly looking at diviner resolutions here. So granted, diviner is not like complete spot on or anything though, but I am not looking at average diviner temperatures either. So I'm going back through the archives and looking at how the temperatures vary from year to year, as well as good as coverage as it can be. But once hopefully Trailblazer and Viper get there, then we'll have hopefully some higher resolution thermal data there.
I think also there's a scale resolution as well. For a large PSR, you may have a single point that has, defines a minimum maximum for a larger area. So how do we account for variability within a PSR as well, beyond just the range at any one point in time? That might be the question, but we can follow up in the chat and certainly during the discussion later, but you may want to follow up with Jen Heldman in the chat window.
All right, thank you.
Thank you.
All right, now we have 2 lightning talks coming up. The first is going to be given by Claudia Pöhler, and it's titled A Geologic Map of the South Pole Aitken Basin Region.
Yes, thank you. So I'm Claudia Pöhler. I'm from the University of Münster in Germany, and I've been working on a map of the South Pole Aitken Basin region for the last years now. The map does not only cover the SPA, but also the South Pole, and we extended it to Orientale Basin to get all the major players in that map. And from that map, I love to discuss any aspects you have of that. We took special care of including secondaries from Orientale. So if you want to discuss that, be more than welcome to join me there. Also, this is part of the GMAP project, where we have the major focus on delivering tools and services for the geological mapping community. So if you are starting a project or want to find out how GMAP can help you, please join me at my poster tomorrow. It's in the polar exploration session. It's poster 9. And whether or not you're on which side of the Atlantic, you can join me at 10 a.m. or 7 p.m. And I would look forward to seeing you.
Wow, that was really fast. Thank you.
I'm sorry.
We have a short amount of time for real quick questions, should someone have one on Claudia's map. Otherwise, we gonna make this quick and move on. Nandita Kumari is up, and she will present on surface illumination temperatures and cold traps at 2 potential landing sites near the lunar South Pole. Take it away, Nandita.
All right, cool. Thanks. This was a great session, and I'm starting with that because while just listening to the session, I felt like we did an internship last year with Dr. David Kring in his SSERVI node, basically, and I felt like we did exactly what we presented in steps. But here I'm like just leaving you with a few results of ours. So we worked on 2 of the proposed landing sites in NASA 2020 documents, and we did geological characterization, mapped boulders, and also looked at the illumination and volatile presence in these 2 sites. Today's talk is mostly about volatile presence and illumination. So I'll leave you with 2 major results from our study. One was that, so we did a comparison of illumination maps in the 4 sites near lunar South Pole. Near lunar South Pole. And we found that though site 001 and 004 has like higher illumination at like few pixels within the 2 kilometer radial exploration zone, site 007 and 011 have like better illumination. So the implication for this would be that even if we have like a fixed power source at the highest illumination location, site 011 and 004 are more attractive, but site 007 and 011 would have like more continuous location. Another major result is like when we talk about cold traps, we have looked at, we did a boulder mapping and we found like a lot of boulders which would act as really small cold traps. So there is a very good chance of like sampling volatiles from these places other than like the large BSRs that are present in these two locations. And I look forward to seeing you all in my poster tomorrow, poster 10, in the same session. Thank you.
Yes, thank you very much. So now, Hannes, we're at the discussion session, which proud to say we're only 6 minutes behind schedule, which I think is pretty dang good. So I'd invite all of the presenters back up to the front of the virtual room, as it were. And while we recollect our thoughts, I do want to take a moment to just, again, remind everyone that we do have this opportunity for poster session tomorrow. Poster session is going to start at 10 a.m. Pacific time, and again in the GatherTown virtual environment that we all enjoyed earlier today. So with that, I guess we'll just open the floor for questions from the gathered throngs of 143 of our nearest and dearest friends here.
I can kick this off with asking a question to Nandita, actually. So do you also plan to incorporate Earth visibility as one of your parameters for assessing site selection? Just because especially in those areas, you might have interferences with some of the large massifs on the other side of Shackleton that might obstruct Earth.
Yeah, I mean, we did look at Earth visibility maps, and you're absolutely on point that we do have those issues. But again, if as in the previous talks, the senior scientists like Dr. Carly Peters and Dr. Brad Jolliffe suggested, we have like a more continuous communication than and like a better, and as we have like, we are getting better and better at preparing elimination resolution, like elimination maps, then that wouldn't be much of an issue.
Thanks, Nandita. I can keep going. I have another question for Brent in this case, Brent Gary.
I also see that Jim's hand is up, so why don't we do
it? Is
why don't we turn it to the floor for Jim's hand, and then Hannes, we can go to your question for Brent.
I actually had one for Brett too. I was thinking, really interested in just thinking about your definition of outcrops. So, you know, some of those boulder clusters look really interesting, but how do you distinguish, you know, secondary cluster boulders at low velocity or exhumed from those that are defined as outcrops? Be really fantastic to see outcrops, but I'm not sure where they're coming from. So it'd be great.
Yeah, some things for outcrops, it's just kind of either bright albedo face and no real shadow. You just kind of see maybe a little bit raised. It could be something that's buried, in all honesty, or it's a bright albedo face in the wall or cavity of like a crater. So something is exposed or protruding out, but it doesn't look like there's something just sitting on the surface like what would be a boulder with like a nice long shadow, unless it's kind of a raised feature with a little bit of a shadow. So it's a little subjective, and I like to go through and just make sure everything's kind of consistent with the definition at some point before it's released. But yeah, so it's trying to distinguish between them is can be a little difficult. Depends on the resolution too.
Yeah, it'd be really great to get that map, and because this could be the key between linking, you know, like for example, impact melt deposits, for example, that are likely to be coherent with other ejecta material, et cetera. So if you see anything in the crater walls or anything like that, that's really fantastic. I'd love to see more details. Thanks.
Yeah.
I'd like to move on with Carolyn, who raised her hand as well. You're muted. Possibly your microphone is turned off because you're not muted in Zoom.
Okay, can you hear me now?
Yes, we can.
I switched to a different microphone. So I wanted to kind of continue on about from what Jim was saying about the boulders. Kind of question for both you, Hannes, and also for Brent. Have you been able to say anything about, like, you have boulders that might have different compositions, or do they all look pretty much the same in terms of albedo, and are they just covered with dust?
Go ahead, Brent.
As far as like kind of composition or anything, it's still kind of difficult to tell. I just been looking at the NAC images. I haven't really compared it to anything else or any other data sets. The geomorphic map is kind of the closest thing we have to like a geologic map there. The geologic maps we have of that area are so broad that they're just kind of connecting any of those features to larger craters than the smaller ones that are there. But yeah, so I think now it kind of, once we have the data sets, going back and looking at the context of where are a lot of these things situated and what could they be? Could they be on the slope of impact melt? Is it something excavated from a deeper crater? You know, is it connected to Shackleton or something else? So those types of things we can start looking at.
Yeah, to follow up on that, as Brent has shown us so beautifully, is that those boulders just they're just a few pixels on NAC, and compositional data sets are very hard to come by, especially at these resolutions in the polar area. Now, and then as was already hinted, like the geology or the geographic context of those outcrops and boulder block locations are the best guess right now. For example, there's a very prominent field of 5 meter or more diameter blocks sitting right on the rim of Shackleton, which is right where my traverse, for example, would approach Shackleton, right where the connecting ridge touches Shackleton. And of course, we could theorize that those boulders might be blocks ejected by the Shackleton event and then deposited on the rim. But other than that, yeah, there's no boulder that I've looked at, maybe Brent, it shows any intrinsic texture, because it's just 3, 4, 5 pixels. Yeah, you can't see anything.
Okay.
Yeah,
that's
not in
what I
the
was
site.
afraid of.
There's a couple larger exposures, and I see the comment from David Crane. There are a couple features that are outside the study area I showed that are impressive, and might have some cool scientific significance and context to go visit. But most of everything else it's in that connecting ridge area that I mapped is a few meters to 5-10 meters wide for kind of the size of the boulders.
Carly has raised her hand as well. Take it away, Carly.
You're muted.
I'm still muted. You're still muted. Everybody's still muted. Sorry.
Okay. Hear me now. Okay. I want to come back to, we are so spoiled with Apollo. We had illumination galore. We could see scattered light in the shadows. Jack Schmidt up against the boulder, he could see what he was doing. We're not going to have that luxury at the South Pole. And we really need to be thinking about how we're going to deal with that. I'm concerned the light level is just not what we're used to, and we've got to prepare for it.
That reminds me, Carly, that we actually have an opportunity to confer with members of the HEO management in 1 minute and 8 seconds as part of the quote office hours session from 1 to 2 p.m. Pacific time in conference room 1. And so, as we all think of issues and concerns, as you pointed out, Carly, I think it's good to that we consider what's actually happening right now at the planning for Artemis. How much would mounted lights contribute to, obviously, okay, we need to be able to work in areas that are shadowed. Let's not even think of permanently shadowed areas, but shadow of boulder, shadow of the lander, shadow of the spacesuit as well. And what operational constraints that will or will not be placed if we have, headlamps, basically. So it is a dynamic environment, but boy, is it going to be exciting to see, as David pointed out in the chat, astronauts meandering through those boulder fields that Hannes and Brent has pointed out.
Carolyn has raised her hand again, or is still raising it. I am not sure.
She may be stretching.
Just stretching out. Now she's now she's getting shy. Okay. One tiny question maybe for Brent. Also, have you considered just using an algorithm automatically plotting a line avoiding certain slopes amount, like let's say 10 degrees, and connecting as many blocks as you can? So like an ideal traverse, if it's just about the quantity of blocks now, just quantitatively speaking, not qualitatively, of course.
So kind of connecting the dots between blocks on like a low slopes, and then trying to connect them as like to a path.
Yeah,
I have not tried
as
that
many
yet.
as you can.
Yeah, that I have not tried yet. So, no. But it could be, you could kind of factor out a DEM, kind of where those locations are, and then do kind of a little traverse plot in GIS, kind of just to see like a least cost path analysis that we were talking about. Kind of, you could mask out where those boulders are located or features are located, and then, you know, constrain a pathway kind of set up in GIS to figure out which would be an optimal way to kind of go visit through them. Is that what you're thinking?
Yeah, and blocking out no-go areas that have unsuitable parameters, like slopes beyond, let's say, 10 degrees, and certain Earth and Sun visibility parameters, and then just connect as many dots within the remaining area as possible. Sort of something like that, a pure quantitative approach. And yeah, and then Dita is already commenting like Jocastra algorithms. Yeah, I know that there are algorithms like that out there. I was just wondering if you considered doing something like that.
I haven't gotten that far yet, and it's one of those things. Once I can release a data set, and then it's other people can do those kinds of fun studies with it too. So that's kind of part of why we're making the data set.
All right. Well, if there are any other questions, comments, concerns, we can discuss that now. As I said, there is the office hours that are being opened up for members of the forum to discuss anything with Jake Bleacher and Julie Robinson, again tomorrow and Friday, tomorrow and Thursday and Friday. We have other office hours with various members of both headquarters and community groups. So please take advantage of those office hours to talk, be discussed with, and raise questions. And thank you, Carolyn and Parvati, for entrusting Hannes and I in our ability to chair a session. I think it went extremely well. I'm really thrilled to see so many participants over the course of the course of the day. The question is raised about how do we get into office hours? If you go through the program is the best place to start, and I believe you have to go through the GatherTown forum to enter the conference rooms to meet with the members of the community. As was mentioned earlier today, or earlier in our session, we are of course meeting at the 50th anniversary of Apollo 11, and if you head on over now to the indispensable Apollo in Real Time website, they are in powered descent. And so I will be happy to stay on and watch along in real time with anyone who wants to, because there's no greater joy than reliving experiences, happy experiences over and over and over again. So I think with that on my part, we'll conclude. Hannes?
Yeah, I have nothing more to add other than a big thank you to all our speakers for a bunch of really awesome talks. It was a real thrill. Yeah, so I don't see any more questions, neither raised hands nor in the chat. So we can call this a day.
All right, thanks so much. Have a great afternoon, everyone. We'll see you all either in the office hours or tomorrow morning, the start of day 2 of the of the Joint SSERVI Exploration Science Forum and European Lunar Science Symposium. Thank you.
See you all tomorrow. Good night and good afternoon.
Because we already have dogs, sorry.
Is there sound to share as well on this?
Noah, I think you're going to have to unmute yourself.
No, if you actually restart your screen share and you select in the bottom left corner, there's a optimize for audio. It'll allow the audio to pass through and we'll be able to hear it.
Can you say that again, Ricky? I was paying attention.
If you stop your share and when you start sharing again,
yeah,
there will be a little checkbox in the bottom left corner to allow the audio to pass through. And you can also check the optimize for video.
Okay.
Nevada, we have negative mission. Roger, negative mission. You got Dory? Roger, what data do you have? Things and ag and Alpha flight. Roger. Restarting this for you. Roger, how's the doctor? Looks good flight. Roger. Ag and things agree very closely. Roger. Dip thrust 9820. Roger, thrust 9820. Copy, flight. You're looking, guys. 20 foot per second. Altitude will go range. No change is what you're saying. No change. That's down tracker north. Roger. Okay, we want to turn. 2 minutes, 20 seconds. Everything looking good. Altitude. Initialize the filter. Roger.